for example, for memory, we can get you the size of the memory operation, or you can extract the raw instruction opcode data, or find something like the nearest symbol if you're running in user mode. Disassemblers are also another good example. There's no point making plugins implement a disassembler for all the architectures when we already have disassemblers for all the architectures built into QEMU. So yeah, that's a feature we provide to them. So let's talk about some of the new features that have been added. So first of all, I'm not going to talk too much about reading registers because there's a talk right after this where they're going to talk about that more. Scoreboards, which is an enhancement of our inline operations. I'll talk about how we've expanded the memory APIs, and then talk a little bit about controlling time. So scoreboards are our replacement for inline operations. So the problem with the original inline operations is they were inherently not thread safe. So if you have multiple threads of execution adding to the same counter, you could lose events. So if you're doing gross measurements of total number of events, it wasn't too much of a problem, but obviously it's not ideal. So now we've deprecated that mode of inline operation and everything is done through a scoreboard. So what a scoreboard is it's a chunk of memory that is dimensioned by the number of vCPUs in the system. And it's also dynamically resized by QEMU itself. So for example, if you're doing analysis on a Linux user program, every time a new thread is created, we'll bring everything to a safe stop, expand the size of the scoreboard, and then start stuff up again. So the plugin doesn't need to worry about doing the management of the memory for that. And what a scoreboard allows you to do is every time you do an inline operation, it's indexed by the vCPU. So it's inherently thread safe because every vCPU has its own set of counters. And then we provide some helpers so you can sum up the counters across all the vCPUs. We've added a new inline operation called store U64. So instead of being able to just add to a counter, you can store an absolute value. And this is useful for doing other types of tests, so you can store the program counter at particular key points or store other information that you want to check at the next block. And finally, we've added conditional callbacks. And conditional callbacks allow you to push more of your plugin down into counters and then only take the cost of a callback when you reach a particular condition. So you can have a decrementing counter and only call the callback when you've had a certain number of events. So the memory APIs, we've now got two. So we've expanded the original memory API to allow you to get the value that was loaded and stored. So we originally didn't implement that just because we were a little concerned about people using that to run around the GPL, but I think that is less of a concern now. And this is the precise way. So if you're interested in every single memory operation and precisely capturing what a particular instruction does, you should use the original memory API to do that. But that can get expensive, because if you're instrumenting every single instruction for every single memory access, that's going to add up to your execution time. So there is a second memory call called read memory virtual address, which allows you to read a chunk of the virtual address space into a buffer. And this is really to be used when you know that the memory you're looking at is unlikely to change. So the key example is when you're about to do a system call, you know all the variables should have been set up, and then you can read the values of those variables out. Controlling time. So one of the things about running an emulation in QEMU is we generally present host time to the guest. And this has a couple of effects. It means if you're emulating a microcontroller, your microcontroller has way, way better performance under emulation than you'd expect it on a real device. And conversely, if you're emulating a big system with lots of application processors, the cost of emulation will eventually show up as the inefficiency of the emulated cores only getting a certain rate of instructions through. So the solution for this in the upstream QEMU is to use a thing called iCount. So iCount is an instruction counting framework. And that allows us to present a virtual time to guess based on the number of instructions we've executed. But iCount is explicitly a single-threaded mode of operation. So I'm sorry, the diagram's a little bit dark here, but what I'm trying to show here is the round-robin scheduling we do. And what happens is we start at the top, we allocate a block of time. Usually it's the number of cycles before the next timer event is going to fire. We divide it by the number of vCPUs, and then execute each vCPU in turn. Now, each vCPU doesn't necessarily use up its full allocation, so at the end of its execution, we have to work out how many instructions it executed, and then update the system time, and then present that. So that's available to the guest. And this means that you get some interesting patterns because you're actually running each vCPU sequentially rather than in parallel. So with plugins, we've added a new API that allows plugins to control system time. So only one plugin can do this, but it can request from QEMU to become the sole arbiter of time. And then all the logic that decides how much time has passed can be pushed into a plugin. This is going to be useful for people that want to do sort of like complex modeling, time modeling of their CPU, where we have absolutely no interest in putting that complexity in the core QEMU code. But you can do that in using the plugin system. So this is inherently multi-threaded. We have an example called the instructions per second plugin. And then that runs all the vCPUs in parallel using multi-threaded TCG. And then as each vCPU gets to a particular point, it either updates the time if time has moved forward, or if it finds that it's run too far, then that thread will sleep whilst it gives time for the other vCPUs to catch up. So this is the first example of plugins being able to modify state for the guest. Just mentioned that you can find other examples of uses of plugins in the contrib directory. So a couple that have come in recent months. The BBV is a basic block vector generator. So this is just generating execution profiles based on basic blocks that can be consumed by some external tools. So there's a tool called SymPoint, for example, that understands these files. Stop trigger is just a very simple plugin that allows you to exit QEMU when you either hit a total number of instructions executed or if you hit a particular address. And that's just useful for running experiments. So say you want to see if a particular instruction ever gets executed, you can mark that in the stop trigger plugin and then give it a corpus of data. And if it exits with your exit code, good. If it doesn't, then obviously that wasn't the change you wanted to make. And then CFlow is a more sort of detailed control flow analysis tool. So you can identify hot branches and where all the heavy return points are in your code. So let's just talk about some potential future improvements. So these aren't ideas that are necessarily going to go in, but some areas that we might want to think about. So the first is, how can we do things on a more semantic basis? So for things like fuzzers, where allocation of memory is important, we need to know things like where is the malloc and where is the free in the code. So we already provide a basic method of getting the symbol information for a given address, but that doesn't tell you enough detail to be able to identify the start of malloc and the start of free. So maybe we want to consider some sort of hypercall. So Valgrind, for example, does this. It adds a little bit of minimal instrumentation to the important libraries. It emits a special sequence of instructions that can then tell the Valgrind core, this is a memory operation and this is the address that you're using. And another thing that we might want to consider for this is having inter-plugin communication. So this is one thing that Panda does, is it has lots of plugins that understand lots of different things, and those plugins can provide services to other plugins, so you don't have to re-implement the logic in your particular experiment. You can just use a constellation of plugins, each concentrating on its own thing. And there were actually RFC patches posted for this a while ago. We didn't merge them because we didn't have a use for them at the moment, but if we start seeing more useful plugins, then maybe that's something we want to consider. We've already got 2 memory APIs, so obviously we might want to add a third. So we have a fast and racy one that can just read bits of memory, and we have the slow and precise one that can instrument everything. But we do actually have the option to do range-based stuff, because QEMU obviously marks out areas of memory for hardware, and we could use the slow path mechanism to be a little bit more efficient and maybe present a range API to the plugin so it could say, this is the range of addresses I'm interested in. Another thing we might want to think about is alternative bindings. At the moment, all plugins are written in C, and obviously we know the problems that can come from writing stuff in C. There's been some interesting downstream examples where people have wrapped a Rust API around the plugins interface, so you can write your plugins in Rust. Whether or not we want to officially support different language bindings for plugins in the upstream, I think is something we want to think carefully about, because that might require us to be a little bit more formal about specifying a proper API. And at the moment, things are moving quite a bit. Finally, and just to summarize, so we now have a core plugin API available in QEMU. There is some interest from the downstream forks of migrating their hooking code to use the core API. I don't think this is going to replace the need for downstream forks. Downstream forks will always want to have the freedom to do their specific thing, but maybe we can reduce the delta, and hopefully that will be beneficial to everyone, both the downstreams and the upstreams. So with that, I think I'm close to time. Do we have any questions?
Several years ago, I was doing the Valgrind port for S390, and some of these plugins thing actually reminded me of Valgrind. And I'm asking myself if we could go much further with that plugin and scheme to do something similar like Valgrind has, where you basically have the intermediate representation in Valgrind, where you can then add instrumentation on top. Would that be powerful enough to go down that path, or is this a completely different set of use cases that you're addressing here?
No, absolutely. I think the Valgrind use case is an interesting one. So I can only speak from my experience with ARM. So obviously the ARM architecture has seen quite a lot of changes over time, and Valgrind has struggled to keep up with the newer architectural updates. But obviously we have a much more complete emulation of the CPU. So what happened with Valgrind is they've got their instrumentation layer, but they also have their sanitizer libraries. And those sanitizer libraries have become libraries in their own right, and now they're used by things like the GCC and LLVM sanitizer plugins. So yes, if we could work out what extra bits of information we need to get out of plugins, we could just then link into the existing sanitizer libraries and then do sanitizer runs using QEMU as a backend for it. And absolutely, that's something I'd like to be able to do.
Have you seen any attempts at abusing the plugin interface for things it's clearly not intended to do?
No, not so far, but I suspect if there are attempts to abuse the plugin interface, they're probably hidden away in private forks inside companies, in which case it's not actually a GPL problem, because as long as they don't distribute it, they can do whatever they want with their downstream. And we already know there are internal downstream forks of QEMU in a lot of the CPU manufacturers, which they use for their modeling. It would be nice if we could encourage them to upstream some of the more useful bits, though.
Okay, so I have talked about plugins inside QEMU. What about using QEMU itself as a plugin in different projects? Like if you want to understand some particular piece of binary code, then you might want to write some unit tests against it or something. And I think QEMU is being used for that.
Yeah, so I mean, I alluded to this when I was talking about Unicorn. One of the problems Unicorn has had is keeping up to date with our CPU emulation, because it's a relatively small project compared to QEMU. I think the cleanup to allow us to build the TCG front ends and back ends cleanly in the upstream project is something that we're actively looking at for doing heterogeneous modeling and stuff like that. And maybe one of the outputs of that could be an officially libradized version of libtcg. But I guess we have to ask ourselves as a project of, do we want to have the maintenance burden of maintaining a stable API for external consumption versus just having a cleaner internal implementation that makes it easier to build QEMU itself? Because obviously when you provide a library, you then now need to think about library stability and how often you change the API for it.
And do you? I mean,
well, for the plugins API, we've explicitly said we're free to change the API whenever we feel, and the best way to make sure your plugin doesn't break is to get it upstreamed into contribs.
But we could just say it's unstable at the moment until we figure it out, right?
Yeah, we could. I suspect we need a few more cycles of it as an internal API before we might want to make it a properly published API. But. Anyone else?
And what about big endian support? I've seen some to-do comments in the plugins where it says, for example, at the register, when you dump the register contents, is this an issue right now in the API, or could it just be implemented?
So we know the big endian mode of loads and stores, so you can query that. And in fact, the latest memory plugin API updates have a system test that work on both big and little endian systems. In terms of the register values, I think you just get the registers in host endian format, which, if you're just looking at the value of it, should be fine because you'll want it in the host endian format for the plugin itself.
Well, unless you dump it, then it's always in host format or order.
Yeah, so I think the execlog plugin tries to make sure that stuff is dumped in the right order, but we've got the information, so it's just a case of cleaning up the plugins to do it. All right, any more questions?
Just some clarification for the last question. Well, the register API actually uses the guest endian, and that is because it is derived from GDB stub API, and GDB stub API is independent from the host endian, so it just uses guest endian.
Oh, okay, yeah, so it's the other way around. We have to translate from guest to host when we dump the value of the register. That's right. All right. Thank you all very much. You can find me on my socials there, and thank you.
Okay. Yeah. I start. I'm I'm from Dynamics Computing and also a PhD student in University of Tokyo. Today I talk about using TCG plugin for microarchitecture research. Okay, so conventionally TCG is used for emulating some kind of hardware design to run a program designed for something defined for host. So for example, you can use it for cross-development or sometimes for also for retro or hobby computing. And this has some common goal, that is to emulate fixed hardware design fast for software. However, today I talk about a somewhat different kind of use case. In this talk, I talk about microarchitecture research, that is to optimize design of microprocessor, in other words, microarchitecture. In this talk, our goal is to simulate various hardware designs instead of fixed hardware design and evaluate their performance instead of executing as fast as possible. And the idea for using TCG for microarchitecture research is to generate software execution traces with a TCG plugin and fit them to simulate modeling hardware designs. Before talking about how I use TCG plugin for microarchitecture, let me describe microarchitecture research and its motivation. The reason to study microarchitecture is to, in short, it is to export more parallelism. However, I'll dig it into the background further. And there is one big assumption called Moore's law. It says the number of transistor doubles for every 2 years. That's quite fast pace. And it's kind of has, this Moore's law kind of has been showing down a bit, but has not stopped yet. So we are getting more and more transistors. The increased number of transistors and smaller transistors actually resulted in direct performance improvement in the past, like before 2006. The smaller transistors allowed to increase the clock frequency. So everything got just faster for each technical generation. And that was really good days, but it is unfortunately no longer true. Transistors too small result in something called current leakage and that causes stopping this clock frequency increase. So we can no longer rely on general scaling for performance improvement. Still, Moore's law is still alive. So we are getting more and more transistors. So we somehow need to find a way to use these extra transistors. Therefore, we need to exploit these transistors with parallelism. That's the main idea of microarchitecture design. However, there's still another challenge called Amdahl's law. So it says if we could parallelize some portion of program execution, some small part of execution cannot be parallelized, can bottleneck the overall performance. And the graph on the right side says even if you could parallelize 90% of program execution, the 10% will eventually bottleneck the overall performance. And so we need to try very hard to exploit parallelism as much as possible. And well, that's not possible just by optimizing software or hardware. We actually need both approaches. With software approaches, we can expose parallelism in program to hardware. For example, you can have multiple threads that are independent units of execution that can be executed in parallel. Or you can also use virtualization, that is to apply one operation to multiple data. With this exposed parallelism, hardware will utilize them and actually contribute to performance. So, for example, for math setting, hardware can use this multiple threads with multiple core or having multiple threads in one core. For virtualization, we can have something called assembly units that has multiple symmetric execution functional units that can process one instruction to that can apply one instruction to multiple data. And even if software doesn't use these features, we can still have something called out-of-order execution that is to execute independent instructions in parallel. With these hardware approaches and software approaches combined, we can file with umbilical law and maximize parallelism. For this purpose, it is essential to understand how software behave and expose parallelism to improve microarchitecture. So that's about the motivation for microarchitecture research. Now I talk about actually how we can study microarchitecture. But the main challenge of microarchitecture research is just microarchitecture is too complex to optimize at once. Namely, processor just executes instructions to top to bottom and does it, but such execution is quite inefficient. So we introduce a concept called superscale and pipeline. The pipeline execution divides instruction execution into multiple stages, and that enables to execute instructions at different stages in parallel and utilize all of the components responsible for different stages. And we can also execute instructions at the same stage using superscale mechanism. Superscale mechanism is to have multiple execution units for one stage, and that improves parallelism. Further. But superscale pipeline is not sugar bullet. It also has some challenge. So sometimes parallelization is not possible because of dependencies among instructions and other reasons. To overcome this challenge, real-world processor makes guesses to exploit potential parallelization opportunities. And that kind of guesses happens everywhere, and we have parallelization and prediction recovery mechanism everywhere. So that complicates everything. So we cannot actually optimize everything at once. For this reason, we need simulator. Simulator is not a real hardware design, but it is it focuses on estimating execution time and sometimes also power and area usage. And with simulator, you can omit details you don't care about from the simulator. So instead of having whole complete microarchitecture design, instead you can focus on a component you are currently optimizing. For example, modern processor has floating point arithmetics, but floating point arithmetics is very complex base, and most people don't understand. But with simulator, instead of actually having floating point as computation unit, you can instead just add some constant latency when you are encounter floating point computation. So that makes microarchitecture research much easier. However, omitting such details means simulator will not be functional. So somehow we need to add the functional aspect from elsewhere. Simulator is also slow. Like it can take whole benchmark execution. It can take months or years to execute whole benchmark. So it is not appropriate to learn to simulate whole program execution. To overcome these challenges, so finally, we get a functional emulator we use functional emulator to generate execution traces. So instead of implementing every computational unit in simulator, we can instead use a functional emulator and gather traces that characterize software. And hardware simulator can follow such traces and sum up latency for computations observed in traces. We can also limit the scope to generate traces to limit simulation time. And there are two called endpoint that automatically finds regions of interest that characterize program execution well. So using this endpoint, we can have reasonable execution simulation time. Conventionally, there are some few ways for generating traces, but they all have some problems with microarchitecture research. A common method to instrument program is to use static instrumentation by compiler. In these days, many people use LLVM for this purpose. It works well for other purposes other than microarchitecture research, but unfortunately, we can't use this approach because it actually alters the instruction stream that's incompatible with the goal of microarchitecture research. The alternative solution is to have dynamic instrumentation that uses normal binary and instrument at runtime. For microarchitecture research, it is popular to use interpin for this purpose. However, dynamic instrumentation has another problem. Dynamic instrumentation exposes the underlying instruction set of the host, so it is typically x86. And x86 is just too complex to interpret, and you will not want to deal with this instruction set in simulator. So yeah, it's definitely better to avoid it. And using host instruction set also means it is hard to extend the instruction set, so it limits the scope of microarchitecture research. Finally, the last option is reference interpreter. For example, RISC-V has a reference interpreter called Spike. But such interpreter has also a number of problems. They are often slow, architecture-specific, inflexible, has limited user space support, and has limited or complicated embedded debugger setup. But TCG, fortunately, solves all of the problems. TCG is fast and supports various architectures. Especially, it's important to have RISC-V that is open and accessible instruction set for microarchitecture research. And it also even has vector extension that also provides various interesting topics for microarchitecture research. TCG has great user space emulation and can work with GDB, so it's so easy to debug. And finally, TCG plugins provide infrastructure to generate enough information for microarchitecture research. Next, I discuss the requirements simulator has for traces. Traces need to capture enough states to simulate. The most basic information is program counter, and next registers, and that one is memory. We upstreamed register API APIs to read registers, and this is available since 9.0. So we can have register API ready. Program counter is the most trivial one, so it's also for DG. And for memory, I was going to say it can only access data that was charged in execution. But the last presentation talked about new API to read arbitrary virtual address. So that means we also have good API for memory reading. So we can generate any kind of information we need for market simulation. We can gather those information at different points of execution. First, we can generate traces at the beginning of the execution that allows to omit program loading from simulator. Another option is to generate traces after system calls. That allows to omit system call implementation. Finally, you can also instrument all instructions. That may be a bit inefficient and have different bigger traces, but it allows to omit every computation from simulator. Then I introduced a shell. There was use case in use case of TCC market share research. In this market share research, I used a simulator called Sniper. I targeted RISC-V Linux user space, and I ran experiments on x86 host. And I used two benchmark trees. The first one is spec CPU that has generic workloads, and the second one is graph benchmark tree that is a graph benchmark tree. Sniper uses interpin the default tracer, but it is incompatible with RISC-V, so it has integration with Spike, the reference emulator of RISC-V. But unfortunately, it turns out Spike is just too slow to run graph benchmark tree. So it is not appropriate for our use case. So instead of using interpin or Spike, we opted for TCG plugins. The first one is basic block generator. We use two TCG plugins. The first one is basic block generator, BBB. That is to capture basic block execution count and characterize software execution. And Endpoint can consume this information to find the regions that characterize program execution best. This basic block generator runs before identifying regions of interest. So it needs to run for the full program, so it needs to be really fast. Fortunately, we had a new APIs called conditional callbacks that allows to instrument only when necessary. So this allowed fast execution of basic block generator, and this API is also available since 9.1. And I appreciate this basic block generator I posted basic block generator to mailing list for upstreaming. This plugin was first developed by a researcher in Nagoya University and named Yocha Nada, and I refined it for upstreaming, and it's almost ready for merge. And with this basic block generator and SimPoint, we can get simulation points that provides regions to actually simulate. So for these simulation points, we actually generate traces using a Sniper front plugin. This traces program counter and register for each instruction. Instead of using a memory API, it infers memory content from registers to match instruction operand and memory data. As a result, I managed to run all gap benchmark set until unlike Spike, and it also passed all spec CPU benchmarks. although it requires few fixes. These fixes are also upstream. So today, the latest game has everything we need upstream. And it provides insights like execution time, bottleneck analysis, and pipeline execution breakdown. Next, I discuss about microarchitecture speculation. So TCG plugin works very well, but there is some unresolved situation. Microarchitecture speculation is execution is guesses made by microarchitecture. There are two examples present here. First one is speculative execution that is based on branch prediction and allows early execution of instructions after branches. However, speculative execution sometimes results in wrong instruction execution. The other kind of speculation is made by prefetcher. Prefetcher guesses the region of memory in the process where accessing and fill caches. And there are some complex prefetcher example called indirect memory prefetcher. It also, of course, fills caches, but instead of just filling caches, it uses the data read from memory to find more pointers to dereference. And this microarchitecture speculation matters, even though they are not present in traces. Traces do not contain any kind of microarchitecture details, so there is no kind of speculation aspect. However, this speculation matters for security and performance. First, it enables, for security, it enables side or covert channel attacks. Speculative execution is exploited by infernal spectra, and the indirect memory prefetcher in AppleSec was exploited with a attack named GoFetch. And it also affects performance since, well, speculation is made to improve performance. Sometimes it can sometimes degrade performance when there is another hardware threat in core because that it wastes execution resource. So microarchitecture speculation quite matters for microarchitecture research. Then let's think about the requirements such speculation poses. Speculation first, indirect memory prefetcher. Indirect memory prefetcher needs to read memory, not access in real execution. So the TCG plugin used to have only 8 places to record only accessed memory, so that was not insufficient. But well, as mentioned in the previous presentation, it seems we are now getting a new interface to read arbitrary virtual address. So I think that API will solve this problem, and now we should be able to implement indirect memory prefetcher with KVM TCG plugin. It should be also noted, dumping all memory is not an option because it just consumes too much data. Gap benchmark switch consumes a lot of memory, so it is not appropriate for that benchmark switch. And next, I talk about speculative execution. For speculative execution, we need to control program counter to execute wrong passes. And it is also necessary to have checkpoint restore to restore the state after wrong execution. And this checkpoint restore is different from usual normal checkpoint restore. Normal checkpoint restore dumps whole states, so it is very slow. But checkpoint restore for speculative execution needs to be real fast. But it captures very small intervals, so that also allows more efficient implementation. These requirements for microarchitecture speculation is very specific to microarchitecture. So so it is not appropriate to implement all of this complexity in QEMU, and instead, so it is more natural to let the simulator drive execution. And in the past, we had something called RevQEMU, but it is now removed. It too much internal details and not very easy to use. And there is an out of tree QEMU fork called Unicorn, but it is out of tree. So why don't have entry solution? So I wrote about what I skip most. Well, basically, we only need to model processor instead of exposing all the features like device emulation for system emulation or system call emulation. So omitting those details can result in much smaller interface that is more easier to use and easier to maintain. So this is conclusion. First, microarchitecture it matters in these days. In days that have more role without general scaling, and trace-based simulation is significant as such microarchitecture research. And TCG is ideal for actually generating these traces. Overall, microarchitecture speculation remains as an open problem. So I suggest you think KVM as a library that hides lot internal details and instead provide minimal API for modeling processor aspect only. And that it, yeah.
Well, thank you for this presentation. It was really interesting. How do you think if you start having something like QEMU TCG as a library, and you start exposing bits of the CPU, how do you envisage modeling things like TLBs that are, I mean, they exist in the CPU, but they don't have an architectural shape? So how do you, and that it massively influences your microarchitecture, of course. So how do you envisage modeling those and exposing them to the rest of the infrastructure in a way that makes it usable and still useful for in general?
Well, I think such aspects like TLB will be will have many application-specific concerns. So I think it's kind of unlikely to make sense to offload such kind of aspect to QEMU. Instead, it will make more sense to implement TLB or more architecture-specific and complicated stuff in simulator instead of having instead of using QEMU. Well, for my usage, well, I'm only concerned with user space emulation, so I'm not really interested in TLB. Yeah, so yeah, for this user space emulation purpose, it's not necessary to have TLB or such low-level architecture-specific concept.
Thank you.
So there is also the story of caching. So performance for microarchitectures varies a lot on how much you can cache. What's your cache replacement strategy? So how do you plan to model that as part of this?
Well, that's also a responsibility of simulator. So simulator records access memory region and because what region is hot and what region is cold. Yeah, so that is also handled in simulator.
Hi. So 2 comments. So I think one thing is that there's probably a spectrum where if all you need to do is extract some information and you don't actually need a full micro-architectural simulation, then the QEMU plugins framework is very good for that. But then as we see in your presentation, like as you need to go deeper and deeper and do deeper simulation, like for speculative execution, now I need an interpreter because I need to go ahead and actually be able to simulate what's going to happen. At the end of the day, then you end up writing a microarchitectural simulator again, and you have all the stuff. Do you see what I mean? Because you can save a lot of work, but that only works when you only need a bit of information. And then when you need a lot, it seems like you'll end up with having a full microarchitectural simulator that's doing cycles and all the caches and all the internal stuff.
Well, I still think hooks will be enough. So, for example, if you have some new instruction, you can just trap undefined instruction exception and implement such new instructions in simulator, and then pass the execution back to QEMU. And I think that would be enough for having more aspects that is not present in QEMU.
Yes. Yes, I think it depends how deep your microarchitectural simulation has to go.
If you design completely defined instruction set that is, for example, completely defined from RISC-V or ARM, then that will be trouble. And you will need your own functional emulator, I think.
The other comment I wanted to make was about QEMU as a library, because it has come up many times over the years. And I think often what happens is that someone proposes it who hasn't been involved in QEMU for a long time. You have, though. You have. You've been contributing to QEMU. So usually, I think the incentives of when that happens is that the core QEMU community says, well, that's not really what we want to do. We want to have, we don't want public APIs that are stable. We don't want to be a library because it just would make life harder for us. And then the person who's proposing it says, yeah, and I don't really want to be a maintainer either. So then it never happens. That could change, though. It's just about whether there is actually enough of a community around it to maintain it. I don't know if anyone is fundamentally against it. It's just that it never happened because the incentives haven't been right in the past. That's my view on that.
Yeah, and fortunately these days we have this GDB stuff and TCG plugin that has some common aspect, like register APIs can be used for this library too. So I hope the extra complexity needed for TCG QEMU as library can be minimized using TCG plugin code and interface.
Okay, thank you. So, hello everyone. My name is Sergio Lopez, and I work as a software engineer in the automotive team at Red Hat. So, I think we should probably start already because we have a lot of things to say and not much time. So, in this talk, I'm going to try to explain a little bit about the specifics and the particularities of the automotive industry when it comes to virtualization. And I'm also going to talk about the work we've been doing over the last year and the last couple of years to get QEMU ready for the challenges that the automotive industry presents for us. Now, to properly address this matter, we need first to answer two questions. The first one is, why would a car need any form of virtualization at all? Because if you are familiar with cars, they are usually driven by microcontrollers. They are also driven by kind of embedded systems. So it seems quite the leap to go from embedded systems all the way to something that actually requires virtualization at all. And the other question is, how is the automotive industry different from any other industries that are already using virtualization? And to start thinking about that, we need to learn just a little bit about the automotive industry itself and the evolution, and the fact that the automotive industry right now is going through a transition period. This is kind of a simplification, but it's just to give you an idea that originally cars mostly look something like this. And MCU is just a fancy acronym for a microcontroller in the automotive industry. And basically, originally cars had a bunch of microcontrollers all around the car, mostly independent. If they are connected, they are only connected to a CAN bus, usually just for logging to events to some kind of central console. But for the most part, it's something that is completely independent. Completely independent devices managing local peripherals that are directly connected to them. In this design, there is a design that works. It has worked for many years, but the problem it has is that it's completely static. The moment the car gets out of the factory, there is no way to alter the behavior of the car, except by physically replacing cars or changing the wiring. And now, another problem with this approach is that the fact that it's so inflexible means that if you have a single automotive platform that you are sharing with multiple models, which is something that the car manufacturers like to do, of course. If you have different models, you need to actually rewire and replace physically those components to be able to offer different experience with different models. And that's probably one of the main reasons why the industry evolved to something like this. In this design, those MCUs, those microcontrollers have been mostly replaced for endpoints. There are sensors, they may be mechatronics, and those sensors and mechatronics are connected to something called electronic control unit or ECUs. ECUs are more complex computing devices than MCUs. They may have firmware, they may have more power, and they basically receive and send events to the sensors, and they may or may not be connected between them. So this is a more flexible approach. You can actually change the behavior of your car by changing just the ECUs or by changing the firmware on the ECUs. But it's more flexible, but it's still relatively static. In this design, you may also have what is called an in-vehicle infotainment system, or AVI. But this is still kind of isolated from the rest of the car. It's something that is there. It's kind of an evolution of the original car stereo. It may show some of the vehicle information, but it's, for the most part, isolated. And from this design, the industry is moving towards to this one. In this one, the ECUs have become some proxies. So it's roughly the same hardware, but the behavior has been moved from the ECUs to something that is called the central control unit. Now, this central control unit is something closer. It's more powerful computing in computing terms. It may have real-time cores. It may have application cores. It may have a GPU. It may have hardware coding and decoders. So it's something closer to what we maybe used to see in laptops, in PCs, in servers. And it's in this design, the CCU is becoming, well, the sensors and the mechatronics are becoming mostly peripherals to the CCU. So this is basically a computer, and everything that's around the car is basically a peripheral of that computing, communicating through the sound proxies. All the behavior, or most of the behavior, is implemented in the CCU itself. And optionally, the IBI can also be running in the CCU. This is optional, but since you have enough compute power, you can choose to also drive your IBI directly from this single board computer. Now, this is something that comes with a number of benefits. For instance, what we have here is mostly a microcontroller-driven design. This was mostly a firmware-driven design or firmware-driven car, and this is mostly a software-driven car. This is something that not everything, but many behaviors of this car can be updated or changed by replacing software components. This comes with a number of advantages. So for instance, you can deploy more complex systems. Many of those cars are actually connected all the time to the internet to offer remote services. So you can check your car battery level, or start up the car remotely, or set up the air conditioning system from your home before going to your car. And also comes with the advantage that you can have OTA updates. You can, if there is a bug in your car, it can be updated eventually by issuing some update the same way you will update a phone or a laptop. Also, for car manufacturers, this also means comes with the advantage that a single platform can easily be used on different car models without having to actually physically replace components if you don't want to. Because you can simply change the behavior of the software, install different software components or replace them, and you will be changing the behavior of the car. This is the reason why most of the industry is going in this direction. Some of the car manufacturers are already there. Some are going in that direction, and they will eventually get in the following years. Now, there are various reasons for going in this direction, but the main one is the ability to have something closer to what is being coined as a software-defined vehicle. Now, before jumping into the topic of in virtualization itself, we need to talk just a little bit about functional safety, which is not the most fun topic to talk about, but we need to at least acquire and clarify some of the terminology, because we are going to see it just in a minute. And basically, from a high-level view, the FUSA is an industry standard that basically allows you to analyze and classify the risks in the different components of a car. It's usually referred as electronic and electrical components, but it also includes the software. The main advantage of this, one of the main advantages is that it provides a common language for different companies to collaborate, because usually a single company, a single car is not built by a single company. You are sourcing parts from different other partners. So you need to actually be able to ask them and establish the safety requirements using a common language. To classify the risk, there are various factors that are factored in, but the main ones are the potential harm to individuals if the component fails, and how sensitive is to timing. And the classification goes from ASIL A, which is the lowest criticality, to ASIL D, which is the highest one. And there is also another classification, which is QM, where no requirements directly apply. Now, the best example, or the one that is used to illustrate this classification, is that an electronic brake system, or EBS, is going to be ASIL D, because the potential harm to individuals is very high. If the brakes doesn't work, it's usually very bad. And the time sensitivity is also very high, because you need to apply brakes potentially in a timely manner. On the other side of the spectrum, as a quality managed component, you can think usually about the ABI, the infotainment system. If you are you cannot listen to Spotify during your trip. It may be more boring, but it's usually not dangerous to your life. So, okay, so knowing that the industry is going in the direction of consolidating hardware and knowing a little bit about functional safety, we can also understand how the most straightforward approach to virtualization in the automotive industry is by simply having a hypervisor and then taking the behavior that was in the ECUs and put it in on different virtual machines inside, on top of that hypervisor. That's the most straightforward approach. You have a statically partitioned hypervisor, and then you simply put your ACLB, QM, and ACLA applications on top of that. Additionally, you are most likely going to have what is called a safety island. A safety island is just a number of cores of the that are in the same SoC, but are running are completely independent and are running a different operating system, usually a real-time operating system. This safety island usually has some kind of control over the application's core, so it can even, in some cases, shut them down or monitor them, whatever. But then again, this is what the first thought then the automotive industry thought got about how to virtualize things and consolidate things. Use virtualization, static partitioning, move the ECU firmware into software running on different virtual machines. But this is not what we wanted to do with CentOS AutoSD. With CentOS AutoSD, we wanted to seize the opportunity that the industry is changing and evolving, to instead of going with something that is purely static, go to all the way to something that it will be way more dynamic and software-driven. So the idea is to not use virtualization at all, which is kind of a weird thing to see at KVM Forum, but the original idea was to not use virtualization and to use containers instead. In this case, every ECU software will be running on an independent container. Isolation will be guaranteed by using container namespaces, C groups, and container technology. We all know about it. And we also are helping in the industry to move faster, which is another really huge concern by the industry right now, because there are newer companies that are able to, well, most of the industry was moving, was creating platforms with a 4 or 5 year cadence. There are newer companies that are moving at that 18 months cadence. So they are developing new car platforms every roughly 2 years, 1.5 years. So it's quite a difference. And by adopting the container approach, we are able to offer users the ability to, instead of develop to adopt all the container workflow and adopt all the container methodologies, to use CI/CDs that are already used for containers, to enable easier testing, easier developing, and so on. So we were happy about that. We were presenting this. Everyone was happy, instead it didn't work that far, all the time. So, for instance, one of the biggest challenges we found is that popular API software, such as primarily Android Automotive OS, cannot be easily containerized. It's not that you can't containerize it, it's doable, but it's very, very inconvenient. Because, for instance, your host kernel needs to be extended to support that particular workload, and it also gives you a kind of a moving contact surface between the rest of the operating system and the IBI. So, of course, one easy way to, or probably the best way to address this concern is to use virtualization. If you use virtualization, you have a well-known contact surface between your IBI and the rest of the operating system. Now, of course, what we thought about doing is putting Android Automotive OS into a VM. And to do that, we first need to acknowledge what are the requirements of Android Automotive OS. So first of all, I think it's important to clarify that Android Automotive OS and Android Auto are two completely different things. despite the very similar name. Android Auto is just this feature that some cars have that allows you to connect your phone and stream and have your control your phone directly from their IVI on the car. And Android Automotive OS actually is a full Android derivative operating system that is targeted towards the automotive industry. It's kind of interesting the fact that applications developed for Android Automotive OS they are developed using a framework that is built on top of the Android SDK. And this framework is targeted towards distraction prevention. So they force developers to build UIs that are not distracting to the driver. And also they are aware of the state of the car. So if you are parked, they can have more interactive UIs. If you are in movement, there are some restrictions about what you can put on the screen. And what's interesting and what's really nice for us is that the reference implementation targets actually a virtual platform, which was originally called Trot. Now, as far as I know, is Cuttlefish Auto. So to be able to run Android Automotive OS, you need to support basically those Virtaio devices. I don't think this list is actually really updated, even though I took this screenshot a couple of days ago. But, well, it gives you a rough idea of what you need. Some of them are easy, because some of them are BSOC-based, which basically means this is a software component that is communicating with another software component that is outside the VM. You also need Virtaio Sound, which was not upstream until very recently. You also need Virtaio Console for Bluetooth, because that's basically a serial device. If you want to have EBS, you need Virtaio Media Video or Virtaio Media, which is basically an interface for hardware coding and decoding. Of course, you need Virtaio GPU, because if you have ever run Android without GPU acceleration, you'll know you are up for a bad time. And you also need Virtaio SCMI for sensors, but also in some cases for power management. And some vendors are exposing power management to SCMI. And we also need Virtaio input, but with touchscreen support. And possibly some others that are not yet here, but mostly those are the most important ones. So when it comes to QEMU, well, the first thing we needed to do is to actually add multi-touch support to Virtaio input, which it didn't have before. And then we started thinking about how to bring and support some of the additional Virtaio devices that we needed. And when thinking about that, we settled on favoring RAS implementation of out-of-process devices using vHost user. And we started contributing and developing to existing or creating new software, new of those vHost user devices, hosting them within the RAS VMM umbrella project. Some of them, such as vHost user SCMI and vHost user Sound, are already merged in upstream in RAS VMM. vHost user media is still in the works, so there are people in the team working, helping getting the specs ready, making a RAS implementation. And for vHost user GPU, which you learn more about that tomorrow in Matej's and Dorinda's presentation, we decided, even though there was already a C implementation that is in the QEMU source code, we decided to, because it was a bit dated, we decided to pick up pieces from CrossVM and libkrun and spin out a different dedicated vHost user device implemented in RAS. And this one with GFS string support, which also we'll talk about it tomorrow. That is really important because VirGL is getting deprecated in Android Automotive OS. Now, the other thing we needed to do, in addition to have Virtaio devices, is to have a way to consume the Android Automotive OS these images. So when you build the system with Android Automotive OS, what you get is basically this kind of files that are more targeted towards flashing them into some device. So we needed to transform them into something that could be easily consumed by QEMU. So we came up with a CVD2IMG, which basically does that job. It takes those images and produces raw images that then can be transformed into QCode2 or whatever you need. And it also embeds the device properties that are required by Android to actually boot the device. And to be able to start everything, because you need to start QEMU, but you also need to start a number of additional components, we came up with a Start AVM that is basically a small script that sets all the stage and is container friendly, because we wanted to run all of this inside a container. And in fact, that's what we did. We put everything into a container using a Start AVM has the entry point. This container will need to link some devices. For instance, we need def DRI for GPU acceleration, and we also need access to a secondary DBOS server. We run QEMU headless, so the SPIAD input is actually managed by a different component that is running in a different container, and it communicates with QEMU using DBUS. And this image may be part of the container or may be provided externally has in some other volumes. There is also the option of having them directly in raw storage and pass that raw storage directly to the container. The decision of when to put the images, it really depends on how the user is expecting to update and distribute Android Automotive OS updates. Now, with this new piece, then we have this picture, and everything seems to be fine now. So we can have the ECU software running in one container, another ECU software in a different container, and or IBI running in QEMU also within a container. So we get both the container isolation and the virtualization isolation. We have, as we said before, a well-known contact surface between the virtualization and the rest of the operating system. So everything looks fine. And in fact, this is where I should be ending these slides. Instead that, and this is a new development. Some months ago, we found that it's never that easy. So in certain markets, it turns out that using virtualization is pretty much a requirement. It's not like the regulation says you need to use virtualization for this particular component, but it's that everyone in that market, the auditors, the regulators, are used to see virtualization. So try, at least for one particular component, so trying to go against the stream is very hard. So at least for the time, it's better to comply. So, but the problem here is that, okay, we should be able to virtualize that component too, but we didn't want to introduce a new development workflow. We didn't want to have a different way for creating VMs, for defining VMs or building VMs. So we put some requirements on this new way of introducing virtualization in CentOS AutoSD. So we wanted to preserve the container deployment and development workflow as much as possible. Everything should be everything should be done through Podman, and it should be compatible with Quadless. These images are not an option because a big part of what we are shipping with CentOS AutoSD is based or is driven by ComposeFS, FSVerity. Significant parts of the value propositions are based on that kind of having everything on a file system. We are also using sign files, sign containers, Delta updates. We will lose all of that if we're using these images. And also, startup time is extremely important. It's extremely, extremely, extremely important, 3 times extremely. If you don't get into the KPIs, into the startup KPIs, you are out of the game. It's game over. There is no, it doesn't matter anything else. So thinking about that, we came with this solution, which is using libkrun for doing the virtualization of small headless components in AutoSD. So for those who don't know it, libkrun is a small VMN written in Rust and provided as a dynamic library. It's already integrated in Podman using through crun. So by using a dynamic library with crun, we guaranteed smaller. We avoid the requirement of a shim, so we have a lower startup time. But we also make easier to switch between different namespaces since everything is loaded by dynamic loader the moment the crun is started. libkrun has an in-process virtualization support, so we don't need to use these images. I mean, this may sound like I'm contradicting myself because just before a couple of slides ago, I say that we prefer out of process because user devices. But in this particular case, a startup is so important that it trumps anything else. So we actually need to favor this, having this kind of speed up. It's also, the fact that this is smaller is also makes it more, give us some kind of future-proofness for the future in case we need to adhere to some future requirements. And finally, this is how it actually looks. This is the final picture for AutoSD virtualization, approach to virtualization. So we have some ECU components running in containers. We have some ECU components running in containers with KRun. So they are actually virtualized using isolated using virtualization. And we finally have the IBI running in a container with QEMU and running Android Automotive OS. And I think that's basically it. So I hope you enjoyed and learned something interesting about the automotive industry and virtualization in this topic. And if are there any questions?
So about the devices, so what were the factors that you're favoring, like out-of-process devices using that VOS user interfaces? Is it the capability to work with other hypervisors or something else?
Mainly that is keeping the VMM small. So I mean, size and complexity, I can make functional safety requirements more challenging. So keeping everything small, and you can get QEMU very small by using building it with modularity. It really favors the fact that we can use out-of-process devices.
Okay, thank you.
Hi. For the AOSP, why you use QEMU instead of cross VM? And do you consider other hypervisors? Why you choose PQEMU? Thanks.
Yeah, that's a really good question. We actually consider using cross-VM for a while because cross-VM was, of course, ready already to use Android Automotive OS instead of QEMU, which you need to evolve. The main reason basically is that our expertise is deeply rooted in QEMU. So it felt to us that we are kind of investing in the expertise we already had by using QEMU. Another reason is that CrossVM is not it's an open source project, but I think in QEMU it's easier to make changes and suggest changes. So it's more open in some senses.
Do you get asked about the QEMU license requirements a lot from automotive vendors?
So far, no. So far, no, because the thing we've been doing with QEMU is that since we are offering as a container, it's kind of a self-isolated component. It's like users and partners may just need to provide the Android Automotive OS images, point it to them, and everything which ships like a kind of isolated component within the whole scheme of things.
So in your diagram, you had the application and RTOS safety island. Do you have any communication between the RTOS and any of the things running in your containers?
They can be through mailbox or yeah.
And is that a standardized thing or a specialized communication?
So far, we are not providing directly any support for that. So it depends on the BSP. Whatever the vendor provides is what we will need to adopt. It would be nice to have something standardized. We saw in the Linear Connect there were some ideas for that, and it would be really nice to have some queues standardized.
Virtio backends.
Yeah.
Do you foresee any requirement for device assignment?
Any requirement, sorry, for?
For device assignment. So VFIO,
yes,
platform
yes,
pass-through? Or?
Yes, it's very likely that we are going to see the need to move VFIO device, use VFIO to delegate network, especially network devices, through VMs running there. And that's kind of a challenge because it's not, in most cases, it's not PCI. So those are platform devices that may require kind of mediated drivers in the kernel to actually be able to play nice with VFIO. But yeah, that's something that we are seeing already.
Okay, we are out of time. Thank you.
Thank you.
Hello, everyone. Thank you for attending our talk. Today, we're going to talk about testing and benchmarking on hardware of hypervisors and operating systems. My name is Sebastian. I am a software engineer at Cyberus, and next to me is Markus. So,
yeah, I'm tech lead at Cyberus Technology. Yeah.
Okay. So let's start. Yeah. Okay, so who are we? Cyberus is a small company from in Germany. So we have about 25 employees all over Germany, and our headquarters is in Dresden in Saxony. And so we have a strong focus on virtualization. For example, we build a KVM backend for VirtualBox. There's a talk tomorrow at, I think, 3:45 p.m. about that by our coworkers, Julian and Martin. So I think you should attend that. And we also built a microkernel-based hypervisor in our early days. And for that hypervisor, we wanted testing on all supported hardware. So, for example, just different generations of CPUs have different features, and we wanted to test all these features that we support. We later switched to Linux-based virtualization, for example, KVM and VirtualBox. But the infrastructure we built for our own hypervisor proved to be very helpful for testing KVM patches, different Linux kernel configurations, and for benchmarking all of that. So over the years, we gathered a lot of knowledge about test automation. And yeah, so Markus will tell you now about our solution to our testing needs.
Right. So what we built is a service that we internally just call SoTest. And just from a very high level overview, what we do is we have a description for what kind of test do we have, what kind of hardware should the test run on, and we have complete bootable OS images, and we want to put these two together, boot them on real hardware, figure out whether some tests succeed or fail, and get the information back as a single decision point for is this change that we just tested, is it good or is it not good? Yeah, that's basically just a high-level overview. We have a package of some binaries and some configuration files. We hand it over to this SOTest service. The SOTest service orchestrates different kinds of machines depending on which tests which machines test are for. We obtain some results that are failures or success, and we accumulate them into a general success or failure. I hope that's not too surprising in the general idea of what you would do when you test stuff. So yeah, we have some kind of web UI. You have individual test runs, and you have individual items in these test runs with a whole matrix of some kind of tests or benchmarks on different kinds of hardware. And what it looks like in the real world is this is a small cutout from our server room where we test different kinds of laptops. You see some laptops in the front here. There are laptops open to 180 degrees in the back, just stacked behind each other. And we have an additional server rack with servers in there, and there are other form factors that we sometimes need to test. And what we want to talk to you about today is the challenges that we encountered and what kind of solutions we found for these challenges. In particular, we want to talk about how we can make arbitrary hardware remote controllable, because not all hardware is designed to be remote controllable. How we can integrate this on hardware testing into the actual development lifecycle. So, for example, how we can integrate it into tests that run for each merge request or for each change. How we enable performance benchmarking. We want to talk about how we can handle throughput issues with this whole thing, because testing on hardware is much, much slower than just testing software and some kind of VM. And also, we want to talk about how we may be able to handle some kind of flakiness in the whole system, so we can have somewhat reliable test results. First, let's talk about how we make arbitrary hardware remote controllable. There are basically three things you need to do to control a hardware in some way that it's useful for a test. You need to power cycle the target hardware. You need to configure what kind of software is going to run on it. And you need to obviously observe some kind of behavior of what the test is doing or what the machine is doing. For power cycling, there are some off-the-shelf solutions for management software for servers, but as you may have seen in the picture, we have a lot of laptops, and laptops usually don't have these kind of interfaces. So you need to figure out some way to do it. If you're lucky, you can do it with switchable power sockets that you can switch off remotely, because some laptops you can actually configure to start when there's a loss of power, if you can somehow circumvent the battery. But also for those, you cannot do everything. And I'm going to show a few pictures here. We have a Raspberry Pi header that we actually use to simulate power button presses by bridging the corresponding contacts either in the front panel connectors that you have in some desktop PCs, or if you have laptops, you sometimes need to solder wires to the power buttons. Yeah, we didn't have to do that for a long time, because in the later generations of laptops, you usually can go the way of do it with the switchable power sockets. But we have quite a few laptops where we have some kind of hole in the case and some wires coming out of them. Yeah, the second part is the software configuration. That one looks easy at first because you can just do network booting, PXE booting. In fact, it really worked well as long as we, so PXE booting in isolation worked really well as long as we were doing microkernel stuff, because PXE booting works great for small kernels and small payloads that you want to boot. But as soon as you get into the area of booting actual Linux images, then yeah, the free memory regions just aren't enough for deploying gigabytes of init-RDs. So we had to figure out some kind of way of loading software after the boot, or if I just have a small initial system that then pulls down a huge squashfs or something. That was a bit difficult, but yeah, it's basically a multi-stage step now, where we even at some point pull down like 10 gigabytes of Windows images for some VM tests. And I think at that point it's obvious that you can't really do that with PXE boot anymore. The last part, the last thing that you need to do is observe behavior, obviously. And here again, we started from a microkernel perspective, where we didn't have a lot of flexibility to implement whole USB stacks or network stacks. So the only thing we really could do that really worked well over a long time was serial. So the old RS-232 serial. And yeah, there's a lot of management to do with that as soon as you have a lot of machines, because at some point you can't just plug all of them into the server directly. So we invested in some kind of serial console servers that abstract them away over network. And another thing we had to do, because again, laptops may not have a serial interface that you can just plug in. And one of the I think the one of the most adventurous thing we did was some kind of Thunderbolt to M2 disk to PCI Express to then serial adapter that at the end helped us get all the necessary information out, the logs and the test results. Yeah, right. So another thing is USB to serial converters, but again, we cannot do them on the whole low level. And this is a piece of the architecture that survived from the microkernel architecture now to when we're doing actual tests with Linux and KVM. I'll hand over to Sebastian again for the next part.
Okay, so now we have our nice SOTES controller, and we can send tests to it, and it will schedule it on the right hardware and report the results back. But as most of you, I think, know, is that the best tool won't be used if it is inconvenient to use it. So you can just let the developer do all this assembling of the binaries and the configuration files. But yeah, as I said, I think this won't be used. So the first thing we did was to integrate it into our GitLab CI. So for every merge request and for every commit, the CI will just assemble everything, push it to the SOTES controller, and report the results back. So for every merge request, we would see whether the change still works or not, and only merge requests where all tests are green will be or would be merged. So this increased our confidence that our products actually work. But as a developer, so if you implement a new feature or you add a new test, you don't want to push every time and trigger all tests just to see whether one test works. So you need a way for the developer to conveniently schedule single tests. And we later adopted Nix and NixOS in our company. And with that, it was really easy to build the same test packages on the developer laptop as we built in the CI. And so, and to select single tests and all of that became kinda easy after some work. So now the developer can just implement a feature, select the test, and on which hardware to run the test, and with a few clicks we can push our tests into SoTest, and this is incredibly helpful. And yeah, so we get our feedback for our features really fast, and this helps a lot when developing new features. So yes. Okay, so the next step is performance benchmarking. So now that we have all of that, we can really do the performance benchmarking because we don't need one coworker that has like 20 laptops and runs the benchmarks and I don't know, writes the results in some Excel table or something like that, because we can just push our benchmarks, because benchmarks are just like tests, except that you don't get it works or it doesn't work, but you get a number that indicates the performance. So benchmarks are a lot like tests. There are just a few differences, but yeah. So integrating that was mostly kinda easy. The things you have to consider is consistency. So you want for every one of your benchmark with the same software on the same hardware, you want the same results. And especially on laptops, this is kind of difficult because if your laptop is in lab mode, it won't, also it tries to be a little bit colder, so it's not so hot on your lab. So if you can't control the hardware, so you can't control whether your laptop is in lab mode or not, you won't get consistent results. And the other thing is that operating systems sometimes need some time to settle down after boot. So for example, if you start your benchmark right after you booted your Windows, your results will be all over the place. So this is another thing you have to consider. But if you spend some time and hard work, you can get some nice benchmark results, and you can see at an instant whether your change increases or decreases the performance. And then you can also have some nice pictures that you can show to your manager. So for example, here we wanted to see whether our KVM backend performs, or how our KVM backend performs compared to the VirtualBox kernel driver. And so the baseline here is the VirtualBox kernel driver, and you can see that the KVM backend performs worse for SEAT and better for NVMe. So you can do a lot of nice stuff with that. So it's worth the hassle. Okay, so now you can build nice tests and nice benchmarks, and if you can do that, you will build a lot of tests and a lot of benchmarks, and you will come to a point where the pipeline just takes a lot of time. And then you have to optimize your throughput. And so the first two things are kind of obvious. So you make some tests and some benchmarks optional, and the developer or the reviewer of a merge request then has to decide whether it is necessary to run a benchmark or a test right now, or whether we can skip those and just merge right away. So yeah, this is, I think, kind of obvious. And the second thing is to skip reboots. So if you have multiple tests that don't influence each other, then you can just merge them into a single test. And because reboots, especially on servers, takes a lot of time and can slow down your CI. So these two measures will make your CI a little bit faster. The next thing is what we call any items. So if we have tests where we think we don't have to run it on every hardware platform because it will behave on all hardware the same, we call it an any item. And yeah, so then if you have a lot of any items, they can run in parallel on different hardware platforms. And yeah, I think this also speeds up your pipeline. Yeah, so scheduling or priorities, this just means that the merge request pipeline has a higher priority than your nightly pipeline. So this won't make your pipeline faster, but at least your merge requests aren't blocked by your nightly pipeline, for example. So yeah. And the last thing is caching. So we know that if we don't change our software, if we don't change our code, we will have the same test binaries. And so into our SOTEST controller, we added the possibility that the SOTEST controller remembers the hashes of a test of all the binaries and the configs and all of that. And if the test controller sees that it already ran some tests, it will just show you the old results and won't rerun the tests. But this only works if you really have the bit-by-bit same binaries and same configurations. So this may not be very easy, but especially with Nix, this is very possible. And then you will have at least a faster pipeline. So yeah, this helped us a lot. Yeah, and the last thing.
Yep. Let's talk about flakiness, because you may have realized there are a lot of moving parts in this. We have a lot of optimizations for throughput. We have the one picture that was like 12 adapters put into each other just to get some serial out of a laptop. There are a lot of moving parts, and sometimes they just fail. There can be network issues, there can be the machines in an unexpected state, it didn't turn off correctly. There could be just hardware issues and you need to replace some part of the 12 adapter chain. And we found it crucial that the test infrastructure itself can figure out whether, for example, the machine that is just running a test does not answer because it is a problem in the infrastructure, in the test infrastructure itself, or if it's an issue of the test itself. It may not always be possible to differentiate between these cases, because the lines between what is test infrastructure and what is actually the software that's being tested are kind of blurred at the point where you load some squashfs after actually booting with PXE-boot. So it's not really always possible to figure out, is this an infrastructure issue or is this a test issue? But I think we found at some point some okayish way by retrying certain tests if we believe it is an infrastructure issue, and we found a certain way. We don't have a perfect answer for that, but that's just a problem that you're going to run into it if you have this many moving parts. Yeah, I mean the issues in the test itself. You want the user to actually realize that there is an issue, and the infrastructure issues, you just want to shield the user from these. But yeah, there's a lot of work going into actually streamlining the user experience at that point, because again, if the infrastructure just throws many flaky tests, just throws failures, and you're just going to hit retry every time, then users are going to lose trust in the infrastructure, and it just doesn't matter anymore, and everything's going to be skipped anyways. Yeah, so sadly not a great solution here, but at least some very mindful thoughts. As a summary, it's a very short summary, but we know that automated testing on hardware can be really hard. But what we found is that it actually pays off. The whole automation around it, being able to just send off a benchmark for some kind of change that you just did, and figure out within, at best, minutes, maybe hours, whether performance changed significantly. You can be able to figure out within a merge request whether there's any significant change. That's actually very useful, especially when going into kernel drivers and when doing very low-level programming. So yeah, that's basically our takeaway from all this. It really pays off to actually invest in this. And I think we don't know quite exactly yet how all this infrastructure fits into all the KVM effort that we are now doing. But Yeah, we are still figuring it out. Yeah, I think that's it. So we can start a discussion of 5 minutes till the next talk.
Couple of questions. So first of all, if you want maybe to have a later discussion about how you can integrate it into KVM QEMU, we have a test framework called HCKCI that uses QEMU KVM for testing power virtualized devices and drivers. So let's talk how we can work together. But I have several questions. So one, do you use Ironic for hardware provisioning? Because then you can use kind of VM images to provide your hardware, and it's part of the OpenStack Foundation's really nice project that you could use.
Yeah. I know of the project, but no, we don't use it. Many parts of this are actually very manually built for better or worse reasons, manually built by us. But yeah, no, we do not use Ironic. It's really just a plain network boot into a few additional downloads.
The other thing, you said you have some problems within those installation drivers. Take a look at HCKCI because we have kind of a lot of code there, including certification installation before, so the Windows drivers installation will be very smooth. And the third thing, gathering crash dumps from the hardware. What do you have some tips? What do you do?
I think I didn't understand.
Crash dumps. So if OS crashes and you have some crash information, how do you handle it?
For Linux, we basically have a whole extra channel where we get the whole kernel log, and we get additional information that is then put into the kernel log. So the logic is basically if something crashes, we have some kind, and we figure out, oh, there's a kernel panic in there. Then there's some time where we still gather additional log, and then we just shut off the test so it does not clock everything because it's still stuck. So basically we try to gather as much information as possible, and then we just shut the test down and go on with the next test or with the retry if the heuristic says, oh, that was maybe an infrastructure issue.
Thanks.
Just a quick question. So how do you recover from the previous test failures? Like, for example, if the system crashed, right? You have to last known good state and recover from that?
Yeah, so the last known good state is usually recreated by powering off the machine completely, the target machine, and then starting it again from a network boot state. You may not always be able to have a completely clean state. For example, if there was something written to the disk, or if there's some kind of other change. But that's basically the only thing we can do. We can just try to cut power, get the machine into its original state, and then just start the next test.
You talked quickly about batching up tests to save time, and I was wondering whether you had a good way of figuring out whether two tests actually interfere with each other in some way, and also whether you maybe got it wrong at some point and that caused maybe, for example, some test flakiness later on and things like that, whether you have some stories to share there.
Yeah, so I think the one thing where we encountered flakiness was in our infrastructure. If you have 10 machines that are downloading Windows images at the same time, then yeah, sometimes the downloads fail because I think at that point we had a 1G connection between the server where the images were and the test machines. Yeah, so there are some issues there. I think for this specific issue, we try to counter it by using torrents. So the machines just torrent some images, and if it's the same image, they just pull it from the source. That sped up everything and also fixed some kind of flakiness issues, and introduced other flakiness issues because torrents are sometimes weird. Yeah, so the whole batching is the machines are largely independent from each other, except they use the same infrastructure to get the tests. So we also only have single machine tests right now, so you can just do one test on one machine. So the interference between the machines is pretty small, I think.
I was wondering also about if you have two tests, how you decide that you can batch these two tests without, for example, rebooting or something.
Oh, got it. Yeah. A trial and error.
Okay, I see. Right. Thanks.
So what drives your decisions about what hardware you're going to test on? I mean, I assume there's a reason why you've put yourself through all this pain to do all these tests on laptops, right?
Yeah. So the decision, so which hardware we test on is largely decided by who pays us for giving them software. So yeah, basically it's a customer requirement. Okay, we need your software to run on this kind of hardware, and then we need to figure out how we do it. I think we don't always have 100% coverage on all the hardware we need to do, but we try to basically do a sweep over all the different architecture generations and everything. So yeah, it's a trade-off there as well.
Okay, thank you. We are out of time.
It's time to start. Thank you for coming to this session. I'd like to start my session. I'm Shunsuke Mie. I'm working at the IGO in Japan. Usually I'm working for the embedded Linux. Today, I'd like to share my recent works that is about virtual device for testing the Linux PC endpoint framework. Let's get started. Okay, I'd like to start with the brief overviews. I'll give you a brief overview of devices that the virtualized. The PC endpoint controller manages the functionality of devices attached to the PCI bus. It is usually equipped with the PCI cards, for example, NVMe, network, and GPUs, and so on. However, some controller has a capability to cooperate with software. In this case, software can mimic any type of PCI devices and mimic with behavior the PCI function. So it is interesting technology and hardware. And I'd like to also explain the framework. The Linux has a framework to support such the controller, which can be cooperated with software. This framework works as the abstraction layer to implement the software-defined PCI endpoint function. And this function, the software-defined function, is called in Linux kernel PCI endpoint function driver. It is abbreviated sometimes EPF drivers. This is the main topic. It is an interesting framework, but the framework and the endpoint framework function driver are not fully matured yet. There are some reasons, I think. One of the reasons is developer and the testers need physical board and machine with some setups. I'd like to solve and I'd like to improve your development experiment. So I'd like to provide an environment that's too easy to set up and run tests and run implement the EPF drivers. And this is my proposed setup for virtual endpoint testing environment. There are two VMs instead of the physical hardware. They are connected via the virtual PCI bus. And I introduced virtual endpoint control devices. And this diagram is the detailed architecture from previous slides. For virtual PCI buses, I'd like to use the VFI user. The VFI user is designed by Nutanix and designed to implement device emulation outside of the VMM on the same host. And it has a client server model. Client works as a PCI host. From the PCI perspective, it is called root complex, and the server works as a PCI device. It is also called endpoint. And communication between the client server is used the Unix domain socket. And for the data plane, the shared memory is used between the VMM guest. And the protocol is opened, so this is a VMware agnostic. From the KVM perspectives, already live VFI user. It is server side of VFI user is introduced and used for multi-process QEMU. So this feature fitted to use case from us. We designed a custom virtual endpoint controller. Also, we can emulating the existing endpoint controller, but I think it has higher implementation cost because the widely used APC has also the root complex functionality on this, leading to large feature sets. And APC has a lot of configuration for various embedded boards. So I don't think it is necessary when considering only the virtual endpoint controller instead of the disadvantage of the custom controller. So we have to require the custom driver for each guest operating system. Although there are downsides, I believe the upside outweigh them. This figure shows the stuff tier and hardware relationship around the QEMU endpoint controller and the drivers. The blue box indicated the newly proposed modules. The driver communicates with the QEMU endpoint controller and the Linux PCI endpoint framework, but the controller is designed to perform a straightforward. So the driver driver has a few tasks. Just receive a request from a framework and pass to the controller emulate QEMU endpoint controller. Next, I will focus on the internal of the QEMU endpoint controller that I'm introducing. QEMU endpoint controller provides the functions to operate the PCI transaction from software. It enables to implement the EPF driver in software. These operations are achieved by the utilize VFIO user or VFIO user. I'll explain one by one. First is handling access to PCI configuration space. This is a process that occurs when the host PCI driver read or write device information or configuration via the configuration space. Providing a way to configure the configuration space is essential for defining the type and information of the device and some sender command from the EPF. This diagram illustrates how the endpoint function driver and the KVM endpoint controller interact with each other using the VFI user. First of all, QEMU APC set up the region for the PCI configuration space that exposes the PCI endpoint function driver. And QEMU APC respond from PCI driver access to the devices, in this case PCI configuration space. To respond this, the QEMU APC endpoint controller, by returning a configuration space values that has been defined the PCI endpoint function driver. So software defined driver define the configuration values that respond the endpoint controller. Next one is I will explain the process of accessing the memory region pointed by the base address register that is in PCI configuration. It is one with the request from the root complex to endpoint memory. It's almost the same figure, but difference is right and the left side. The memory region located on the RAM, on the endpoint controller, a root complex PCI device driver access to the region. To realize this using VFIO and the QEMU APC respond to request from RC. And we have finished explaining the processing of requesting using from the root complex. And next is the following slide will focus on the request from the endpoint. And this is a handling request to accesses RC memory. It is commonly known as a DMA because the memory read and write request from the device side, PCI endpoint side. Instead of setting the callbacks, in this case, we used the memory sharing using VFI user. PCI host memory region can be mapped to the VMM process that works by the VFI user, and the memory region is mapped to the guest on request from the EPF driver. After that, the guest operating system access the root complex memory transparently without any callbacks and transaction. The last one is interrupt. It is method to notify the host driver to device, in this case endpoint. If I use a facility, the exchange interrupt notification using event FD. So we just call the VFU setup device in our reset, and after that, we can write the interrupt, the API named VFU trigger. The internally the event FD is updated and notified to the root complex side drivers. Now that I've explained all of the feature and how to realize them, so I'd like to move the demo part. And for the demo, following tools I used. There are two VMA. One is a cloud hypervisor for root complex side, and the second one is a QEMU for endpoint side. Because cloud hypervisor has a verify your client, and QEMU has a verify your server side. So we just use them, and I introduced the devices, that is virtual APC device, and operating system Linux is used. And to testing, we used some drivers and tools. It is PCI PF test and the PCI endpoint test and PCI test. I explain detail more. Dig into the detail. This shows the overview of the testing. There are two VMs and connected between the verifier user over the Unix domain socket, and loaded the APF driver and the PCI driver on the left side, root complex side. As a result, the PCI endpoint test, PCI driver, and the PCI APF test driver communicate over the verifier user. Let's show, before showing demo, I explained some flow of the PCI EPF test. So what we will do, in this sequence figure, I omitted some PCI endpoint and controller and some drivers. Just shows the PCI endpoint test and the host driver. First of all, host driver set up the payload to transport and calculate the hash, and write request command to send the endpoint bar region. After that, the PCI APF driver detects it and start the command. In this figure, what I want to say is, in this transaction, they for processing, one is the configuration read from the root complex left side, and memory accessing to the endpoint side from the root complex, and the DMA from endpoint and the interrupt. So let's start a demo. They are split to console. It is corresponding to the right side and left side, respectively. Sorry. So I will run the QM at the right side, and I will run the cloud hypervisor on the left side in the terminal console. This is a command to execute the QEMU. Key point is following. It is a device that we introduced and pass the parameter to represent the Unix domain socket that create the verify user. run QEMU and Linux as a guest. And as you can see, the QEMU PCI endpoint control driver is already loaded and set up the PCI endpoint function for testing. This command shows the set up the PCI endpoint function. In this script, set up the PCI device ID and vendor ID and bind the software-defined function to the controller and start up. I forget to give a permission. Let's try. Run the Linux. Set up the endpoint function, and we can see the socket that's created by the QEMU APC. And next, run the root complex side of hypervisor. In this case, use the cloud hypervisor with this argument. Key point is here. Use the VFI user and connect to this socket. Also, RCSI Linux is launched, and most bottom one, the devices, PCI devices that shows by the right side over the VFI user, and a kernel module is loaded that is PCI endpoint test. So let's communicate with this test module. The PCI test is provided by the Linux kernel, and -R means testing with read, and -S means the 1 kilobyte transportation in this test. After that, we can see the operation name and the payload size and OK. This means the transportation value is correct with verification. So I think it works well. And finally, I have some tasks to upstream. The remaining task is first is some fix buggy code, and DMA control emulation is required. Not necessary, but EPF cover the DMA transmission for testing. We need to implement it, And for the QEMU, we need to also implement the live migration. VFIO support the live migration, so it is not difficult for me, I think. And that's it. Thank you for listening. Do you have any questions, answers, or suggestions?
First, thank you for the talk. That was pretty interesting. Sorry for asking ignorant questions. So I'm neither familiar with VFIO user too much, nor with the EPF code in a Linux kernel. So if I got it right, when you access memory mapped memory of a PCI device via a bar, so you need some kind of shared memory between the QEMU process and the other side, right?
Yes, you're right.
Yeah. So this shared memory resides in the guest on the EPF side, or is it in a QEMU host process?
Yeah. Actually, the mapping of the shared memory is processed in the VFIO user.
So that's part of the QEMU process, or is it part of the VM that runs in the QEMU?
Is on the QEMU process.
Okay, so it's QEMU process. So QEMU has full knowledge where the memory resides.
Yes.
Okay. Okay, thanks. That clarifies my question. So I was wondering whether there's an IO MMU required between the guest's memory or something like that. But okay, that's fine. Okay, thank you.
Thank you for your question. Okay, there is no questions, no suggestion. I'd like to close this session. Thank you for listening again.
So hi everyone, my name is Alice Frosi. I'm a principal software engineer at Red Hat. And today we are going to talk about debugging technique using virtualization and containers. So for those of you that are not familiar with QEMU, Kubernetes allows some extension of its API and functionality using custom resource definition. And QVirt is actually one of those. So QVirt allows to enable, define, and deploy virtual machine in Kubernetes cluster. So when we think about debuggability, usually think about you have your laptop and you try to reproduce what is going on, wrongly going on locally in your laptop. This is, of course, not possible with QEMU because you need a Kubernetes cluster. And the virtualization stack is also deployed in a way that has some restrictions. So this has some challenges when you want to either use certain tools or try to understand what is going on. So first of all, Vir stack is deployed in an unprivileged container. So that means that libvirt and QEMU are running in session mode, and they are run as with UID 107. So they are deployed in containers, so it means that they have been deployed in an isolated environment. So this basically means they have their own PID and mount namespace, for example. Additionally, especially for unprivileged container, you give the minimal set of capability to those containers. So, and this, for example, prevents certain tool to work. Additionally, QVirt images are distroless. For those of you that are not familiar with distroless images, basically those are container images without a package manager. So as regard of debugging, you cannot install on the fly some missing debugging tooling. So that makes hard to have your own preferred tooling in this kind of environment. So we are not running on our laptop. We need to run on a cluster because this is how QVirt works. So based on the cluster and the roles that you have in that cluster, you have different capability granted. So if you are a cluster admin with high privileges, so you can, for example, deploy privileged containers. But if it's not the case and you are considered as a regular user, then probably your visibility, for example, is limited to your own Kubernetes namespace. So you cannot, for example, inspect core component like QVirt component. So all those restrictions plays a role when you need to understand what is going on. So don't be scared. This talk is exactly about this. So for the first command that I want to mention is kubectl. So kubectl is the Kubernetes client command that has various subcommands that help you in deploying container. And certain of those commands can also help you to debug. So for example, the classical and standard way to try to understand something, what is going on in your container is basically execing inside the container. So basically this creates, for example, a shell inside the same container namespaces as your original one. As far as it regards QVirt, QVirt has already included in the image a couple of tools that can actually help you to understand what is going on with the guest. So for example, we have Virch inside, so you can inspect the status of the guest, the XML, or we have also virtadmin. We will see this also in the later slide, but this allows you to change the login level of the virtualization component. Something that is also included into the Virt launcher is QEMU. And of course, this is very useful when you need to inspect these images. So those you already get because are already installed inside the container image. So let's suppose that you have cluster admin. So you have this superpower in the cluster. So what can we do? So first of all, as I already mentioned, you have visibility in all the Kubernetes namespaces, and you can start privileged containers. We will see this in a second. So kubectl, again, has a subcommand called debug, and you can target with this command specific nodes. So you can deploy the container image that maybe contains additional tooling. And basically, these commands create a pod for you where you can attach and has already different things set it for you. So for example, it's running in the same PID namespace as the host. So for example, you are able to see all the processes that are on that node. Some other thing you can see is that the root file system of the host is mounted in this directory. So under host, you can, for example, inspect the release. So this is something that you can get easily with this command. However, the pod that is deployed using this command doesn't have the privilege flag set it for you. So certain operations are not allowed. So for example, trace is one of those. You cannot attach to a running process. So here on the left, you have an example, and you can see that I have set it in the security context, the privilege equal true, and we are running as root. So for example, doing this, we are able to, again, getting the QEMU process and maybe attaching to it with trace and start looking what QEMU does. Something that is also possible when you run as privilege is directly executing commands into the host. So as we saw, the file system of the host is mounted inside the container. So what you could do is basically chroot into in that directory, and basically you are directly on the host. So for example, in generic Kubernetes distribution, we have tooling like cryctl that allow you to inspect the containers, and you can use it exactly to see what's going on with your container. So in this case, we are using cryctl from directly on the host. For example, to inspect and find some libvirt directory in this case. So certain debugging tooling requires to have the target debugging tool binary. And again, from container, this might not be possible, or it might not be available. However, with QVirt, you can know exactly which QVirt release you are target to and which QEMU binary you are target to. So you can get this information from the QVirt custom resource definition. So this has some fields like observed deployment config and version. So basically from this environmental variable, you can exactly get the image that is deployed in your cluster. So once you know that, what you can do is referring that QVirt image. So Virt launcher is the image that has libvirt and QEMU inside. And basically from that version, you can copy it in your debugging container. So basically you can see that we are referencing this as a launcher. And here basically we are copying the QEMU binary inside the debugging image. So this is the way how you can reference, and get exactly the binary, the QEMU binary that you want to target for debug. So something a little bit easier. We, of course, want output. And the QVirt output level determines also the libvirt and QEMU level that will be printed on standard output. Of course, there are various changes how we can tune this. So QVirt works for using annotation. So annotation is a very generic mechanism how we can customize and pass additional information to pod. So QVirt has this annotation, libvirt log filters, where you can actually specify and tune the logging level of each component. So if you annotate your VM with this, basically you could increase or decrease the logging level of each component. So this is done at startup time. If you want to change it dynamically, how you can achieve this is basically, again, using kubectl exec. And as I mentioned, inside the image, we have virt admin. And basically, we can change the logging level using that tool. Not only that, but we can also redirect to a file. So virt admin is able to specify a file, like here. And then kubectl has also something called copy that basically allow you to copy a file from a container locally. So you're able to inspect it locally. So something that QVirt has a feature called QVirt sidecars that basically allow you to modify on the fly the libvirt XML. So why do we do this? So QVirt has an API, and based on the VM definition, this basically implies a certain XML. But we don't support all the possible options that libvirt offers. So a way that we invented to allow users to customize the domain XML are exactly these sidecar hooks. So this is useful, for example, to try new feature or maybe even for debugging. So again, we need something called config maps. So for those that don't know what a config map is, it's basically a Kubernetes object that allow you to create file inside the container. So in this way, in the config map, basically we are creating a Python script that modifies the XML. If you want to use this config map with QVirt, again, you use an annotation. So on your VM definition, you can basically specify the sidecar hooks with the config map that contains the script that we want to run to modify the XML. So this is the most complex setup that we are going to see in this presentation. So please stay with me. But this is exactly an example of these sidecars. So let's suppose that I want to trace QEMU inside Virt Launcher. So as we said, we are using distroless container. So I don't have trace inside Virt Launcher. So how am I going to start QEMU with it? Another thing that I want to stress is that I cannot run QEMU and then attach to trace. This is not possible. I will get permission denied because that requires high privileges. So, but what we can do is start trace and QEMU as a child. So what I want to do is that libvirt, instead of starting directly QEMU, it will start trace plus QEMU. So this is the goal that we want to achieve here. Okay, so the first thing is how I get my debugging tool inside the container. So QVirt has something. So Kubernetes has something called PVC. You can think about a directory that you can populate. So what I wanted to do is provide a virt launcher, a directory with my debugging tool. So how do I create the content of this directory? So what we can do is basically using a Docker file. So you can see here that I'm referring to CentOS Stream 9 because it's exactly the same base image of a virt launcher, and then I'm installing strays there in a directory. Additionally, I will also copy in that directory a wrapping script. We are going to talk about this in a second, but basically it's this file here. Okay, so I have installed strays with a dependency in this directory, and basically what I need to do is copy the content of this directory into the PVC. Okay, so this is the way how we bring additional binaries and additional file inside the virt launcher pod. Okay, so we have talked about the sidecar. So now I want Liver not to start directly QEMU, but to start a wrapping script. So my wrapping script is actually this one. And you can see that it's basically strays with some output and QEMU. Okay, so now basically what I need to do is modify the Liver XML instead of calling directly QEMU here to calling my wrapping script. So and then when I click and launch the VM, basically Liver is not going to start QEMU directly, but it will start strays plus QEMU. So this is actually, I know, a bit complex way, but it's a way how we can customize and debug this immutable environment. Okay, I hope everything was clear. If not, please, in the Q&A, ask me more detail. So, sometimes we have images that have not completely or correctly been installed. So we want to inspect and see what is going on with this image. So I hope many of you are familiar with GuestFS tool. And QVirt has also a client called virtctl that has support for GuestFS tool. So if you call and use virtctl, GuestFS, and the PVC, PVC is basically a directory or a block device. Basically, this creates a container for you. And this container called GuestFS pod has already the GuestFS tool inside. It mounts the PVC in the right directory and also set up a couple of environmental variables. So you are actually already ready to debug your image. So here we have an example with virt rescue. So basically you can give to virt rescue the image, and maybe you need to fix the initRD using Dracu. So basically this is what the example is doing. So memory dumps. So if there is something going on your guest, you might want to dump the guest memory and inspect what is going on. So again, we have a support for this in QVirt. And again, we use the QVirt client. So virtctl as a command called memory dump. And then basically this command will create a dump for you. So how this work? So you have virt launcher with libvirt inside and QEMU in your guest. So Kubernetes pods are very static, so it's not possible to add dynamically new volumes. But QVirt has this functionality. It's something that we build on top. It's called a volume hot plug. And this is one of the features that we are using here. So we are able to dynamically attach a new volume. We'll get the dump there. And when that is finished, so you can monitor also the status of the dump from the VM status, we can detach it. So something that also we would like to get is, because right now this is sitting in the cluster, is to download it and have it locally. So this is, again, another feature that QVirt has that's called export. So basically, using hot plug and export, we are able to dump the memory of a QVirt VM in the cluster and get the output locally. So something, again, useful is, of course, getting the console of your guest. This can be done in different ways. So VirtCTL has support for the serial console or for VNC. So this is if you need something interactively, or something else pretty nice, in my opinion. There is another container inside the Virt Launcher pod that's called guest console log. So basically where we redirect the guest output. So if you are familiar with Kubernetes, then you basically just get the container log. So you get the logs as a standard container. So I would like just to mention a couple of nice Kubernetes debugging technique. So kubectl logs and kubectl describe allow you to get the log of the pod and also to get more information about the pod. So if your pod is not going to work, those are one of the commands that you want to use immediately. Something nice is kubectl port forward. So if your container doesn't behave properly, then maybe you get the port is not reachable, something like this. You can use this in order to forward the port locally and inspect what is going on. kubectl debug we have already seen for the node, but this command also allows you to start additional container in a running pod. So this might be something useful, again, for debugging. And something nice is checking the events that are happening in your Kubernetes namespace. So basically, those are a list of events that happens for different resources. So this kind of give some kind of history. That's good to know sometimes for troubleshooting. So for QVirt, a couple of other tricks very quickly. So QVirt supports different annotation, and those two are pretty useful when you want to debug something that maybe your Virt launcher crash. So the first one basically keeps Virt launcher pod running. So the standard behavior is usually when QEMU exit, also Virt launcher exit. But sometimes you want to inspect the environment. Maybe there is a permission denied or something not set in properly. So this is quite nice. And the second does the same, but for migration. So for migration, usually we have two pods, one for the source and one for the destination. Basically, the two libvirt. And yeah, if there is something not working properly on the destination, then you can use the second annotation. So VirtCTL also has port forward, so the same, but for if there is a port not properly working on your VM. VirtCTL ADM log verbosity allow you to change the verbosity of QVirt component. This is something that maybe it's helpful for you to debug QVirt itself. And if your guest has the guest agent, the QEMU guest agent installed inside, you can get the information using, again, VirtCTL guest OS info VM. So I hope that this was useful for you. It was mostly an overview of what is possible and what are the problems. And yeah, just keep in mind, try to understand what are your role in the Kubernetes cluster, and kubectl and virtctl are your debugging companion. So Thank you for your attention. Do we have any question?
So you showed how you can have this annotation that gives you the sidecar hook script, which is very nice and integrated. But then for the wrapper script, for example, you had to create your own container image and add the script and everything else. Is there a chance that we can have something like that for a wrapper script integrated in a nice way, the same way that the sidecar hook is, so that people don't have to fuss as much? Because that looked like the worst case scenario for setting up the debugging environment.
So for the script, yeah, the problem is it really depends on what you want to achieve. So and the wrapping script is like some additional debugging tool. For example, for those example, I needed also strace binary. So you need something opaque. It's not something that you can support easily.
Arbitrary
Yes.
modifications. But could we make the most common use case, like install an additional package in a known base image, basically, and add the wrapper script? Could we make that smoother?
I think so. So there is something called OCI artifacts that got alpha in Kubernetes 1.3.2 or 1. Sorry if I'm mistaken the version, but pretty recently, that allow you to basically reference a container image as a volume. So basically what you could do from that slide that I show, you create your Docker file with all the things, and then you can reference in the content from a volume. I think that will make that setup much easier.
Hi. I had the impression, based on the examples you gave, that most of the debugging happens post-mortem, like when you run strace, you direct to a log file. Does it change too much? Is it possible to have some kind of live debugging, like GDB or something like that? What are the challenges for that?
So GDB, actually, I tried to run GDB with the -s option, and I failed because liver was not. QEMU was just ignoring that option. But what you can do, instead of starting QEMU with strace, you could start with GDB. And then you can have a local client and connect to it. So basically...
using GDB server, something
yes.
Like that.
So I have some reference, and you can see that, and I exactly explaining also the GDB, how you could do GDB interactive session.
Okay.
It was just more complicated for the slide, but it's already explained into the in the QVirt user guide. So we have also the GDB example.
Thank you.
Hello. I noticed the latest KubeVirt 1.40 alpha version based on the Libert 10.0 and QEMU 8.2. So my question is, this version is behind of the latest Libert and QEMU version. So my question is how to debug the KubeVirt failures based on the latest QEMU and Libert version.
Do you have any specific way how you would like to debug? Because it's about the output, or
just use the latest Libert and QEMU version. Maybe is it possible to build this water launcher or image and so on?
you need to build Virt launcher with the latest QVirt and QEMU, but this is about building. It's another complexity. But theoretically, what this work should work with all the versions. So I'm not sure, or are you talking about upgrading Virt and QEMU for debugging? Is it that the question?
Okay, thank you.
Okay.
So we are out of the time.
Okay, thank you, everyone.
My name is Michael. I work at. Oh, yeah, there we go. I work at Akamai. I think most people know what Akamai is. I'm surprised that some people do, some people don't know. We are not known for our KVM interest. It's mainly known as a CDN business. But about 2 years ago, we purchased Linode. A lot of people don't know what Linode is. It's a small-ish cloud provider. But we're mainly known for our CDN, but it kind of made sense for us. We got into cloud a couple of years ago. We bought Linode, and it's been fun. We're a medium, moderate-sized cloud with just about 500,000 VMs. So it made sense for us because we run a lot of software in the edge. So running virtualization in the edge was kind of a natural extension. And we've learned a lot in Akamai. So what are we doing with QEMU? We try to live migrate whenever we can, but like a lot of cloud providers our size, we simply cannot live migrate. We would like to. It's always best case scenario when we can because you get milliseconds of downtime, but most of the time we can't. We just don't want to keep spare capacity around that costs money. Sometimes we just can't because of silly things like CPU flags, security restrictions. Akamai is probably one of the most secure companies I've ever worked for, just security at every level. And we just simply can't live migrate. That holds us back sometimes because we want to roll out software much faster. We want to reduce the amount of stranded capacity that we have. We'd like to start rolling out software updates to hypervisors daily, weekly, and sometimes we just can't. It might because of some of the restrictions. Maintaining double the space or even fractions of extra space in the cloud is just not ideal. So we started looking into live updates. It actually surprises me quite a lot, even myself, my boss, when we started working on this, that live updates are now possible. So instead of live migrating, what is live updates? So this means as of April, I believe, Some patches were merged into QEMU, so thank you to the QEMU community from Oracle. There was a demo of this working from a gentleman named Steve from Oracle. If you look that up in a KVM Forum a couple of years ago, I believe, when it was still virtual. And another demo in Plumbers, I think maybe 3 years ago from Google, if I recall correctly. When we saw those presentations, we really paid attention that this, so live updates is the ability to update the kernel, the host kernel, and all of host userland without live migrating at all. So the VMs will never stop, and they just continue. There's a small amount of downtime, and I'll get into how that works in detail. But you're able to update the entire system minus firmware. You're not able to update obvious things like your BIOS and that sort of thing that actually do require a power cycle. But if you don't need a power cycle, you can live update everything in place without a live migration and still get the benefits of staying up to date, keeping your hosts up to date. So I'll get into exactly how that works. But it continues to surprise me how many people don't know that this is possible. It is possible today. And it potentially would save us as a business millions of dollars because we don't need to maintain all of this extra capacity. So again, thank you to the community for getting that merged just recently in QEMU. So how does it work? The key enabling mechanism to do a live update is some way to keep guest memory in place. So there's really only one way upstream in the kernel today to do that without changes or without carrying a patch set today that we're using now called persistent memory. This is a bit of an unusual use of persistent memory. This is usually designed for actual persistent memory, physically persistent hardware, persistent DRAMs. You can buy these kinds of DRAMs that will stay powered on, either with a capacitor or something like that, or some other mechanism that will actually persist your memory. But we're not doing that. This is what we call emulated persistent memory. So you start the VMs in some pre-reserved location in RAM before you start the kernel. You ask for this memory to be reserved. You run the VMs out of that memory. And then using the new feature that was just merged, again, just a few months ago, so it's pretty fresh in QEMU 9 called Checkpoint Restart. Again, that was some work from Oracle with the community. When you turn this on, you tell QEMU, instead of allocating anonymous memory, it now allocates file back to memory in this persistent location. So I won't go into the details of this. PMEM has been in the kernel for many years, so that's what we started with, and I'll talk more about that. But that's how you enable it. You then do a kexec operation. So when you're ready to do the live update, you switch to a new kernel. You tell QEMU, before you switch to a new kernel, you tell QEMU to do to save all the device state, IOMMU state, VFIO state is all preserved in a file the same way it would happen with a live migration or a suspend to disk operation. You save all of that state, synchronize all the file systems, quiesce all of the devices, and then perform a kexec operation. So this is right in the middle. You switch over to a brand new kernel, or potentially an older kernel, depending on what you need to do, and also potentially a brand new user land. So we do that as well in production. We're actually running this, rolling this out to production as we speak. We may update the entire user land if possible, if you need to. We often do need to. New kernel, all new user land, kexec into the new kernel, and then the VMs are sitting in persistent memory. So for potentially seconds that I'll describe later, they have been paused as compared to a live migration where they may have, at the end of a pre-copy iteration in a typical live migration, they may have only been paused for milliseconds. In this case, they will have been paused during the entire kexec operation. So I'll show some timings on that in a little bit. But once the new kernel is taken over, we then just reverse everything that we did before. So bring online the new QEMU, potentially a new version of QEMU if it's a new user land. We have to do quite a lot of extra bookkeeping that we were not prepared for, so I'll get into some more detail there. We have to reconstruct all of the C groups, file descriptors for vhost if necessary, invert IO, and finally bring the new QEMU back online. So this actually works. I meet a lot of folks who just, even managers myself, who tell me every time, this works? Seriously? it does work. It's pretty cool. I didn't know, in fact, before this KVM Forum, how much work was going into TDX and SEV. This is very interesting in that context too. We just had some talks on that because you don't need to live migrate all of this massive amount of state potentially. There's so many use cases for this, even outside of the cloud, in other virtualized environments. So it actually works, and it's pretty cool to see when it's going. Just a little bit of this. Again, it works today. This is what the QEMU command line looks like. So if you've never started a VM from a file-based location, that's how you would do it. Using a different memory backend than QEMU up here in the middle. And then you just need to specify a few capabilities and parameters to QEMU that are different, telling QEMU not to allocate from anonymous memory. So instead of that, it's allocating from the location that you chose in persistent memory. So it's pretty easy to use. That's kind of the easy part, but it does work. So how does it perform? This is where it starts to get interesting, and delineates who can actually use this or not. So the kexec is fast. Bringing the VM online at the end is quite fast, but everything in the middle is where the headache starts. I've worked on kernel teams for a while, and most of the time I talk to my coworkers, I ask them, have you ever done a kexec before? They've all said, yes, we tried it, but it took too long. That's a common answer that I get. And it's still true today. In order to do this, all of the devices have to be reinitialized from scratch. And that's often a deal breaker for a lot of folks. In our case, we started this on an internal cloud instead of going to our public cloud first. We control the applications that run on our internal cloud, so that's a caveat there. And we see device initialization times around 5 seconds. This is just vanilla devices that we don't control, that we have to work with vendors on, that go into our boxes. And our software can tolerate this. TCP can obviously tolerate this. Your TCP connections, if you have a live update and a VM is down and vCPUs are not running for that many seconds, they will be fine. So you're not going to lose any connections. It's just, but there are some weird problems that happen inside the guest, like time stopping. Time stops moving forward the entire time. So you have to think about that. If your application is sensitive to the management of time, you have to deal with idiosyncrasies like that. So, but yeah, this is a very long time for nothing to happen for a virtual machine. So if it's not able to deal with that, most software can deal with that. It's just a matter of working with the owner of the software. So then the next biggest problem is everything after system boot up. When we first started implementing this, we simply could not tolerate the amount of time it takes to go all the way up to system D and all the way up to user land. It's just so much wasted time. System D starts all the way over here at the end. We could not wait that long to bring a virtual machine back online. So we start our VMs immediately when the init MFS starts, as soon as possible. Just skip everything and start the VMs as soon as possible. So libvirt is gone. Systemd is gone. Everything's gone, so we have to deal with that. These are just kind of surprises that you have to deal with just for the cost to get the VM online as soon as possible. So that's not too hard to solve. It's really, the really hard problem is the device drivers. But that's where we are, and it does work. So 10 seconds or less, 5 seconds or less, depending on what system we're running on, we can get the VM back online roughly that fast. And we haven't had a problem with that with the VMs, the software running the VMs that we use today. That's kind of, if you were to use this today, that's kind of where we are today. So I'll talk more about that. I encourage questions. We've had a lot of very interesting discussions on how to solve this, and that should be quite a fun topic. So I mentioned some of the challenges. We have one more significant challenge to talk about. So when we started testing this, there were surprises that anyone else testing this would have to deal with. I'm going to save the first one to last because it will lead naturally into the end of the conversation. So serializing C group information. Because we're starting so early, we have to save all of the C group settings and restore them again. Anything that libvirt came up with when the VMs were starting, we have to reconstruct all of that, and that's not ideal. So ideally, there would be a libvirt solution for that. That would be great. I think I mentioned we have to recreate file descriptors for VFIO, and every queue in a multi-queue VirtIO NIC has to be, all those file descriptors have to be recreated. We started doing loop testing, and that was fun. So instead of, the idea here is that if you get really good at live updates, you live update way more often than you live migrate. So we have to simulate that. So when we started doing this, we would just run live updates in a loop for days, hundreds of times, over and over and over again. And you have to do this because if something goes wrong in QEMU, some tiny little bug that you've never seen before, well, now you have a VM running forever. It may never be turned off ever in the future. We have VMs running for 5-6 years without ever being turned off, which sounds crazy, but these VMs exist, and you have to be prepared for that. So there were many cases where a device, a physical device, would be fine after 50 or 100 live updates, but the 200th time it was reset, it gave up because whatever the firmware author wrote for that device was just doing something that happened to persist across 200 resets, and it actually stopped working. So that was a surprise. You have to deal with that. I mentioned this one already, Systemd. We decided to just skip it. I've seen articles about people starting Systemd in the initramfs, which is just more software in the initramfs. But we need to skip as much as possible to get the VMs online. So whatever you have to do is okay. We found a lot of firmware bugs, and we don't have the time to go to every vendor and say, hey, we found a bug in your firmware after 200K execs, can you fix it? And a lot of times they're just like, well, this was designed to be power cycled. Why are you contacting us? Leave me alone and don't ask me for, that's a common response when we reach out to a vendor in this kind of context. That sucks. I think I mentioned timekeeping as well. So that is a complicated problem to deal with. If there were a way in KVM to kick QEMU and somehow signal to KVM clock or something to correctly adjust for whatever the TSC is telling the guest what its time is, if there were an automatic way to do that, that would be super helpful. So a lot of the things I'm bringing up here are kind of call outs to the community that if you do this in production, this is what's going to happen to you. Time just stops. The clock just doesn't advance 5 seconds later. So if there were a way for KVM to, through some kind of an upcall or whatever, to get the guest to update its clock accurately with the amount of time that has actually passed, that would be great. So that's a problem that happens today. Regardless of the clock source, if I remember correctly, that's a problem today. Another very important feature of, and this is quite important for us with live updates, is NUMA support. NUMA support, NUMA pinning, and CPU pinning are critical, very performance critical for us. We have to have it. So what we do is that we may have VMs running for years. We need to move VMs from systems that are that don't have live updates enabled and live migrate them seamlessly to a live update compatible system that can then finally perpetually run live updates. Old VMs, we have to be able to support that. So we have patches for that. Thank you to the community again for working with us there. We quite a lot of challenges. So again, talk to me offline if you're curious about some of that. And this is my last slide. So persistent memory is quite a challenge to deal with. We're representative of a smaller cloud provider, and we don't have the ability sometimes to dedicate SKUs, whole bare metal SKUs to specific products. So when we want to differentiate some VMs from another, as our cloud is developing, and I know this is true, I used to work at DigitalOcean and IBM, as the cloud gets bigger and organically grows bigger, you don't always have the ability to dedicate specific types of hypervisors to specific products. Sometimes that's just not even possible. So when we do, this matters particularly for NUMA support, we need to be able to move a VM from one NUMA node to the other live. We need to be able to swap VMs live while they're running out of persistent memory. And we need the ability to resize the persistently allocated region live as we change the definition of what that hypervisor is without having to tear it down. So there are a lot of solutions for this. I think I'm running out of time, so please come and talk to me offline. There are a lot of solutions for this on LKML that are quite interesting. And I think I missed a column, particularly the case where we need to move VMs between NUMA nodes on the same host. That's quite common because our hypervisors are not dedicated to specific products. So if we send a customer's virtual machine to one NUMA node, we can't live migrate sometimes, so we need to be able to basically defragment capacity across the fleet of machines so that we can make space available on an individual system that might be available in the future for a future VM that might arrive in that slot. So we have to do cross-host bin packing sometimes. And if we can't move VMs between NUMA nodes, then we can't do that bin packing. And if we can't do that, then the persistent memory solution gets in the way. So again, we're using PMEM at the top, and there are some solutions, additional solutions here that might work for us. So that's the end of my time. Please, any questions? I think we have a minute left. Oh yeah, thank you. Yeah, so we have a few minutes left, and please do find me. I continue to be surprised about how many people don't know that you can live update today, and so it's quite interesting. Go ahead.
Yeah, so the time progression thing definitely should, if I understand the problem correctly, that definitely should be workable. Maybe there's just something in QEMU that it's not adjusting a TSC offset or something like that. But to understand the problem, are you saying that that live update time, for example, 10 seconds just disappears and the VM doesn't see it advancing? Is that
it doesn't see it advancing, exactly.
Okay,
exactly, yeah.
We should take a look at that because there definitely is a way to apply an offset and serialize that across K. Exactly.
There is, in fact, in the clock implementation in QEMU, it applies an offset at startup. but there's no way to reapply it. And so in QEMU specifically, so it's just not a complex fix, but it is.
And there are a few more things I just want to point out. So in your case, you're not doing device assignment. There's a whole another can of worms if you want to do device assignment and state pass-through, and I think that's another part of this problem.
Yeah, and I think that's representative, to answer that question, it's representative of a lot of cloud providers that are this size. All of the clouds I've worked on in the past didn't use it, and so as a community, getting live update support more easier to use, we have to think about that.
And those characteristics that you speak about, like swappable and all those kind of things, become less interesting or even undesirable when you're starting to do device pass-throughs.
True.
So,
right.
Just jumping back to the time thing, don't you have to solve the problem of just that's too long of a blackout period, though? Like, yeah, you can make it look to the guest like the time was correct, but if you don't have a response for 10 seconds, you're going to have so many other problems downstream from that.
We haven't found that to be a problem. We were surprised by that. I mean, I was expecting that when I first started doing this to be a big problem, but most software can handle it. I mean, most software can handle it. There are some isolated cases, yeah. You do have to. The answer is yes. If it's a if a customer has a contract with your cloud for millions of dollars and they can't handle it, then you're gonna have to deal with that.
The time problem is surely not that different from what you face if you do save and restore to disk.
Correct.
Because your VM is running. It's just not running for a very long. So in that case, when we restore from a saved file, there's a QEMU guest agent option where you can just poke it to update its system clock. I don't know if that is
I have to look into that.
Useful or not. My other thought was all the tricks you're doing in the init Ramifest to bring things up before systemd and libvirt. That's very brave.
Yes, it was a pain in the you-know-what.
Particularly with the C group stuff, I'd be pretty worried that systemd might decide to just blow away the whole hierarchy and put it back the way it wants.
It tried to.
It starts up.
It did try to. We found a way to hide ourselves, but it did try to. Yes, and in fact, as well as libvirt, we are cheating and not working with libvirt instead of against it. So I think I spoke to Martin about that. Ideally, there would be some kind of a libvirt binary that didn't require bringing in the entire libvirt userland that could just get us going, and then when systemd came back online, it would then reestablish its knowledge of the VMs.
Yeah, it'll be interesting. I mean, I think in the initRD, on Fedora at least, you've got systemd in the initRD. It then when it finishes the initRD, it then re-execs the real systemd. So
yeah, that's a problem. It adds another second. Like every second that you add, even 1 second, even a half a second that you add is too much. And so unless we can find a way to really just whittle apart systemd into some essential component that would get out of the way and just have the startup, it's a hard problem. It's such a big piece of software. So good questions, yeah.
I was wondering, so this looks definitely very impressive, and just to echo some of the points that were brought up earlier with how like 5 or 10 seconds downtime might be an issue for some
it can
workloads.
be, yeah.
Have you been following some of the other things that have been going on with like local exec or live migration for QEMU specifically that's being discussed at the moment? Like as a little brother, you don't get the kernel exec, but on the other hand, you get basically a lot less downtime and a few other headaches that you don't need to solve.
Yes, that was merged. Oh no, pieces of it were merged in QEMU from Steve.
The other stuff is still, I think, under discussion.
So that's a good. I mean, I guess that'll round out our. Hopefully, we have more time. I don't know how much time we have, but there is an extension to the changes in QEMU that don't use kexec. So everyone check that out. They're good patches.
Unfortunately, we are over time. So
all right, thank you.
So hello, my name is Maciej Szmigiero. I work at Oracle at Linux Virtualization and Security team, which is actually part of the Oracle Linux organization. In terms of my upstream work, I usually work at KVM and QEMU. In terms of upstream stuff, I'm the maintainer of QEMU VM bus support and also of QEMU HV balloon driver, which is kind of like a Virtual balloon, but using the native Hyper-V Windows protocol. But this talk is totally unrelated to Windows. It's also about mainly QEMU, but it's related to live migration of the device state. So what's the current situation here? In terms of the current live migration in general is mostly done using a single main migration channel. So there is only like the main migration channel, and all the data which needs to be migrated between the source and the destination QEMU has to go via this single channel. Obviously, that's not very good because, well, it doesn't scale very well. And we have this is especially problematic during the so-called switchover phase. So for people who are not, let's say, live migration specialists, basically the live migration in so-called pre-copy mode works that way that the source QEMU transfers as much as possible to the destination QEMU. It switches the virtual machine, which is still running by this point, into a state when it basically logs all the data, dirty data that it has changed, and then it tries to copy those data too. And at some point, the count or size of this remaining data is below certain limit. At that point, the source VM is stopped and the remaining data is moved to the destination QEMU, which then the VM is restarted, or you better say resumed at the destination QEMU. The main data that needs to be transferred is obviously the guest RAM image. But this is not the only data that needs transferring. Also the state, or let's say all the what's in the actual QEMU devices, both the devices that are emulated by QEMU, and in some VMs you have the device which were passed through from the host, usually called VFIO, and that's also can have their own state. And here the talk is mostly about the state of those VFIO devices. So using a single channel in 2024 is not very good, because you obviously have multi-core SMP systems, and single channel usually uses only one core, one CPU. So whether this is a theoretical problem or the practical, there are devices which have very large device state, which normally if we have like emulated QEMU devices, their device state is really tiny, so their transfer times is not really big issue. But for some devices, this is really a major issue. For example, there are some VFIO smart NICs. Those smart NICs are basically the small computers which are separate from the main, let's say, main server or main computer. And all those devices state has to be transferred to the target device. Obviously, you also have GPUs which have their own video RAM, which could be huge. So I'm not a GPU specialist, so I might be wrong here, so sorry for this. But I think that the problem is very similar on the GPU side. So what's the example of that kind of device? This effort was developed against a Mellanox, or NVIDIA those days, Connect X Smart NIC. And this device has 128 gigabytes of RAM. This is not a RAM on the host, but the device has its own RAM. As you can see on this, under this heatsink is basically you have like a small computer, or pretty major computer with 128 gigabytes, and all those has to be transferred to the destination. And this, even in the small setup, this results in like hundreds of megabytes of device state per VF. This device, by the way, could be divided into virtual functions. So you can emulate like 4 different network interface cards from one device. It can happen. It can support even more, but this talk is about up to 4 for the reasons I will present in later. So why this talk was developed against this card, and the measurement will also be done against this card. It's most of the optimization are pretty generic and could be applied to any similar device or any device with the large device state, and some even are could be applied to any device state transfer. So we have already a kind of we have already a special framework for transferring transferring migration data via multiple channels. This is called multi-FD, and it was introduced in late 2017 in QEMU 2.1 by Juan Quintela. I hope I'm not mispronouncing the name. And he said that the migration stream becomes CPU bound by about 10 gigabytes per second, which is slow by the current data center NICs, which are at least 100 gigabytes per second, and there are like 250 right now. And also there is the issue is that this multi-FD is only for RAM transfer. It cannot do any kind of device state at the current its current state. It also simply what it does, it basically queues all the RAM pages which need to be transferred to channel threads, and those only this sending and receiving actually happens in parallel in those threads. This is very easy to implement because basically reading and writing guest memory is simply reading or writing to some QEMU host virtual address, so it doesn't need any kind of specific locking. There is some problem with synchronization, but this is like a minor issue in comparison to extending it to device state transfer. So another, to be clear, the metric that this talk is about and which we are trying to optimize here is to reduce the downtime. The downtime is basically the time that the VM is stopped. This is the time when the source has decided that it needs to switch to the destination, and this remaining data is transferred. And after this time has passed, or after all these things are done, the VM is stopped. And for how long this is stopped, that's called downtime. So what kind of problems we have? We have the problem that if we have a single migration stream for all these multiple devices, then obviously introduces interlocking between different devices, because those devices are saved and loaded in order as their device state is being transferred in this single main migration channel. So if we have like a multiple VFs, then obviously it means that there is no parallelization between those VFs. They have to happen sequentially. You can theoretically improve this situation. You can call it fix it by decoupling the data transfer from actual reading and loading. But this will be like a partial solution. And as far as I know, nobody has proposed anything like this right now. And also not the actual, let's say, loading and reading also not only happens on the QEMU side, but also we have the device firmware and the kernel driver. And until recently, the kernel side wasn't even pipelined. So when the source QEMU was reading from the file descriptor, the device wasn't actually providing the data state wasn't read from the device. And so basically, only recently, there has been a part-set merge like a year ago by Mellanox or NVIDIA that introduced double buffering for at least this Mellanox VFIO driver. So now the reading from the devices can happen in parallel with the QEMU reading from kernel. This is already upstream. And obviously all the QEMU improvement wouldn't help us much if we have like a bottleneck in the device or the kernel side. So you can argue that all those changes has to happen, let's say, sorry for the pun, but in parallel with kernel changes. So the current, how the currently QEMU does, what kind of channel it receives is based on the basically a heuristic based on the early data read from the channel. If it matches some magic number that this is the main migration channel, if it's not, that is main migration sorry, if it's not, then it's the multi-FD channel. That's obviously not very flexible. So the first version of the patch set actually introduced some kind of channel headers. This is not actually my design, but also from Avichai Horon from NVIDIA, that introduced an explicit channel header which says what kind of channel this is. Unfortunately, this wasn't very well received upstream, so for now we have to live with extending the existing migration bit stream instead of, let's say, ordering this. So the first version of the patch set also has a dedicated device state transfer channels. So there was basically a set of channels dedicated to sending device state data, and different channels send only RAM data. This, from, let's say, basic test, it shown that it did improve the downtime sometime, about 14% improvement. But at the same, the theory here was that since the device state channels don't transfer RAM, they don't have to participate in the RAM sync process, which is basically a kind of like a synchronization point between those multi-FD channels. But at this time, I didn't have a automated testing tool, so all those tests were just done very, let's say, primitively. So I had to develop some kind of tool when I could do more reproducible tests and find a way to actually remove those channels because they are kind of unwanted. It turns out this is actually, it was possible to have like the same performance with shared channels. But the actual, one of the problem is that if you have too many multi-FD channels, then apparently there is, not only you don't get benefit, but apparently things actually getting worse. So you basically have to tune the number of multi-FD channels to your workload, which is not great because you don't want to have that kind of like a manual tinkering to have a good performance. So at some point, probably it would be good to understand what's the problem here. But the good thing is you can have the same performance without this shared channels. Sorry, without this dedicated device state channels. So they were removed in the next version. So what's the current design? There is a one-to-one mapping between threads and number of VFIO devices. That's both on the loading and, sorry, of the reading and the restoring loading side. So there is a loading reading thread that reads the device state from the particular device. This is, as I said, per VFIO device, and then this is queued for the next free multi-FD channel to actually transfer to the destination. And on the loading side or receiving side, you have there is a thread that takes those buffers, and when they are ready, as there is a problem with the current firmware and kernel interface, that those buffers has to be restored in order. So once you have all the previous buffers loaded, received and loaded, then you can restore the next one. So we have to have a kind of reordering thread in order not to block other devices and not to block the receiving multi-FD threads. So because of this buffering, there is some kind of let's say, almost unbounded. It's actually bounded by the total size of device state, but this wasn't really well received during the patch set review. So there is the next version had actually number of when the administrator can configure the maximum number of the buffers that are in the destination not yet loaded. So if this is exceeded because, for example, there is too much reordering on network, then the migration will basically fail. So there are quite a few threads in this design. So in the current parsed version, those loading threads are in the multi-FD managed thread pool. It's technically possible to use actually fewer threads than devices, although this will almost certainly negatively affect performance, so it's not a good idea. The details are still being discussed with the community right now. The problem was that QEMU did not have like a generic thread pool. The only thread pool in utils was for AIO, and this wasn't possible to directly reuse for just generic worker threads. My last attempt actually introduced a generic thread pool, but it was suggested that it might be better to actually reuse the glibs ones instead of creating a new generic thread pool in QEMU. We need to have some kind of extensions for this thread pool. For example, neither the QEMU AIO nor the glib one has a wait function, which basically waits until all the threads have done its work. So it might be a good idea, that's still being discussed, whether to actually add this new method first to glib, to this G thread pool, and then use it in QEMU, or to open code in QEMU. That's about the loading thread. Rest of the threads are still managed by the device itself, which is, well, it's unclear whether actually porting those old threads to thread pool has any sense, because it's basically one call in the code. So probably the number of boilerplate code would exceed any kind of benefit. So this is like a debatable whether this makes sense. So there is also another thing which is not with parallelized, which is the device state change. The VFIO devices have some states when basically tell the device what they can do. For example, whether it can actually run and produce a dirty data, or it can, for example, has been stopped. So only one of those device state changes has actually been parallelized, like happen in a different thread. Rest of those basically happen still in the main migration thread. So for devices that do a lot during this state changes, it might be good to have them in a separate thread too. So there is also a problem that, for example, basic VM state also needs to be loaded in the main migration threads, because it uses the main core QEMU address space methods, which then basically explode when they are called from some different thread. So this also could be fixed long term, but by having them thread safe or reentrant. So that will probably give also some more polarization, so lower downtime. So let's go to the benchmarks. That's basically the source machine. The configuration of the VM is up to 4 VFs. Unfortunately, due to the limitation of the setup, I wasn't able to test more than 4. It's up to the issue with dirty tracking with those devices, that they support up to 4 dirty tracking or live migration up to 4 VFs. If someone wants to have more than 4 VFs during a VM, it has to rely on basically on machine dirty tracking, which is only possible on either on AMD machines or Intel machines from Sapphire Rapids, I think so. But unfortunately, this machine doesn't. It's too old for this. So up to 4 has been checked. That's the configuration. It has about 100 megabytes of device state per VF, and the benchmarking methodology was running multiple runs of the same VM because you have to basically catch the VM in the situation when it's idle. Otherwise, you are measuring not only device state transfer performance, but also the performance of the RAM transfer, which is wasn't the point really of this exercise. And the guest wasn't restarted between those runs, but obviously it has to be restarted or launched again if we were to change the configuration of those guests. For example, change the count of the VMs. Sorry, VFs, not VM. It usually took about 30 live migration for downtime to minimum downtime to stabilize, but I did like 70 or sometimes even 100 just to be sure whether I'm not missing something. So with 6 multi-FD shared channels, that's basically the downtime improvement with this patch set. As you can see, basically it scales more than linearly with number of VFs, which is I hope it will be at some point we reach a state when the device transfer is almost you can, for example, transfer 4 VFs at the same time as 1 VF because there is no bottleneck on the transfer and loading side. But it's not. We think it's not only about the transfer or QEMU side, but it's also on the device itself that it's not internally parallelized as well enough as it should. So, but it's still, we think that, let's say 67% improvement with 4 VFs, it's worthwhile as a starter. And you can see that it doesn't really break anything, and it's a small improvement with 1 VFs, but it's good that there is no regression, because that's usually what we are worried when there is improvement that only touches the how things scaled. That it might improve the scaling, but usually often it breaks the small case. But in this case, you can see that the small case has improved a bit even. So as I talk, there is some issue with number of channels that you have to tune it yourself. You can see that this is kind of counterintuitive, that with more multi-FD channels, you actually get worse performance, especially on the median and the 75th percentile. You obviously you want to have like as wide, let's say, good performance band as possible, and you can see that basically the performance roughly stays the same to about 15 channels. Above that, you can get it. You can see that it gets worse because this additional channel not only don't bring any benefit, but also actually cause some issues. For example, slow things down by extra unnecessary locking or so. So that's something that we would like to also eventually work on to be as count of channels independent as possible. So what's the status of the patch set? The version 2 has been posted. Version 3 will be posted soon. So hopefully this will make QEMU 9.2, but we'll try as much as possible, but this is like our target right now. There are some also issues with current QEMU migration code, because it's basically a sync code that doesn't return to the main loop until everything is done. That severely makes it harder to introduce any performance benefits. And also on the kernel side, we would love to have a like unordered VFIO device state loading that would simplify QEMU side a lot, but this is not current state, and this would require actually changing the VFIO user space API, so it's kind of hard to do. Obviously, I would like to have like a generic parallel VM state transfer, but this is also very far in the future. I've been also asked whether it's possible to introduce the live stage device state transfer, which is the state that doesn't impact downtime when the device is still running. That's something we have also on mind, but it's also, like, let's say, a very far future direction. So since we have only 5 minutes remaining, I will ask for if anyone has any questions. Yes.
So for that one VF numbers you report here, how many channels you're using?
This one?
Yeah.
6. It's 6 channels.
Oh, it's all 6 channels. Okay.
Right.
Okay, I see.
Because you can see that this is the lowest downtime. I actually, I think that if you go below that, you get worse numbers. You start getting worse numbers once again. That's why it uses 4. Okay. Sorry, 6 channels.
Okay, and another question is, so why do you want to listen VFO device state because not ordered? Because I mean, the VFO device state is just a black box to you, right?
Yes.
But why you care about the ordering?
Because the device needs to be loaded. Device needs it to be loaded in order. Otherwise, the device would basically fail the migration. That's the problem currently. We want the device to accept it in any order, but the current device and also current VFIO user space API says you have to load it in order.
It's a stream, right? It's just a
it's a separate buffer. It's a stream, but you cannot just take a chunks of this stream and reorder those.
Yeah, that's why it's a stream, right?
Yeah, but if you send it by multiple channels, right? Then those chunks can get reordered if they arrive on a different channel in a different order.
Okay, I see.
It's not only parallelization, like you have multiple devices and you have like send data from those devices into separate channels. You also take data from one device and send it on the multiple channels.
Okay. Yeah. Thank you.
Naively, I just don't know. How is there 100 megs of device state per virtual function?
Basically, those smart NICs have like, not only there are full computers in itself, they basically have a lot of offloads. They track the state of, for example, IPsec, state of network connections of the host, and that's a lot of data. And I think those devices that we are talking about, they also do RDMA in InfiniBand, and there is a lot of state related to this.
So you have multiple channels for transfer the virtual device state. Is this transfer data traffic mixed with the RAM traffic? Or?
Exactly, that's shared channels. That's what they are. They mix the RAM transfer data with the device state.
Okay.
That's currently only happening during the switchover, which is the VM is stopped. I've been asked to also look at improving those transfers during the VM is still running stage, but this obviously wouldn't touch down time. So there is like a little, let's say, performance sense of this is limited. You will obviously have a probably quicker migration time, but the VM is still running, so it doesn't matter that much.
So so you show that there's optimal number of the queues for transfer the device state. So I think if when you open a new channel, there must be an overhead. This overhead may also offset the performance benefit when.
Exactly, that's what happens. If you have like too many channels, your overhead starts to exceed the benefit, basically.
Yes. So thank you.
That's something we'd like to, not happen, because we would like people to just stuck with the default configuration, which I think is 15 channels, and it might not work 100% best, but I think it should work at least the best possible for 15 channels. So we want to have this like a performance band or performance set of performance configuration to be as wide as possible.
Okay, we are out of the time. Thank you.
Hi everyone, I'm Rohit, along with Manish and Tejas. We are from Nutanix and working in Acropolis Hypervisor India team. So today we are going to talk about virtual machine, memory over commitment with the help of user fault FD. So this is the agenda for today's slide. So first I will be talking about background and current challenges with memory over commitment. And then Manish will talk about our new design and its workflow that will try to overcome those challenges. And then finally, Tejas will talk about result and future work. So now let's start with the background. So memory overcommitment allows hypervisor to allocate more guest physical memory to virtual machines than the available memory present on the host. So there are two most popular methods through which it is done currently. That is ballooning and hypervisor swap. In ballooning, hypervisor interacts with the guest or driver present, like balloon driver present is as a guest, and it inflates and deflates basically based on memory pressure. Also, in hypervisor swap, guest pages are swapped out to disk, which frees up the memory that hypervisor can use for other VMs. And also, these pages can be swapped back in whenever they are required. Now let's see live migration with memory over commitment. So in live migration, we transfer the dirty pages of guest from source to destination, iteration by iteration. But in case of memory overcommit VMs, pages can be swapped out to disk. So to transfer these pages, first we need to transfer it to memory, swapped in to memory, and then it will be transferred to the destination. Now let's look at the current challenges associated with memory overcommitment. So, so when live migration touches, live migration touches all the guest memory. It causes page fault on swapped out pages. These page faults basically increases data transfer throughput for live migration. And slower data transfer give guest more time to dirty pages, which in turn slows the data transfer, creating a vicious cycle that overall increases the line migration time for memory overcommit VMs. Also, when line migration touches a page, it makes it hot, and to allocate memory for that, we may need to swap out some guest active pages, which may fault soon. This disturbs the working set of guests, causing both guest and live migration performance. Now let's look at the another challenge. So with current native memory overcommitment, there's a lack of control over overall swap process and where to swap out pages. So we need to have a final control over these pages to make that can help with making custom optimization for our hypervisor. For example, like having full control over swapped out pages and its location can help in design optimal swapped theory with multiple swap devices. We can also make swapping process lightweight by removing the bloat that we don't need. Also, we can set swap policies specific to each VM. So if you have control over swapped out pages, we can use multiple swap devices and optimally decide where to transfer, where to swap out pages based on its hotness or coldness. Since faster devices are expensive and offers limited capacity, so we can transfer the warm pages to faster devices like NVMe SSDs and transfer the less warm pages to slower devices like SATA SSDs or hard disk drive. Now Manish will talk about our new design and its workflow that tries to overcome these challenges.
Thanks, Rohit. And hi, everyone. So how do we overcome these challenges? So our idea is to have a user fault FT based user space memory controller, which gives us full control over guest memory address space. And now what is user fault FD? User fault FD is a Linux kernel feature, which allows handling page faults at user space. And these page fault events are posted by kernel over FD. User fault FD allows handling page fault events for both page missing case as well as page write protection. And whenever any process has page fault, it has to wait until that page fault has been resolved by user space. And one thing to note down is that also for guest, we support async page fault so that impact of page faults is reduced. And one thing to note down is that user fault FD provides control only over page fault path. It does not provide any control over native Linux swap out path. So this is a high-level summary of our design. First thing we do is that we disable native Linux swapping for the QEMU process. Then there will be an external process, we call it MEM controller, which takes control of full QEMU guest memory address space. Idea behind keeping it externalized that we get full independent control. QEMU will be using shared memory allocated by MEM controller, and both MEM controller and QEMU will be communicating over a Unix socket-based communication channel. MEM controller takes control of all the address spaces with the help of user fault FD. Once MEM controller has the control, it can basically decide how many pages to swap out, where to swap out, and from where to take page fault from. One detail is that we haven't yet integrated ballooning in our design, and that is something targeted for future work. This is how initial setup looks like. It is a two-step process. In step one, QEMU will ask MEM controller to create a memory region of given size. QEMU will just tell how much memory it requires. Physical limits on that, like how much physical limit we want to put on that memory region is something decided by MEM controller dynamically, and it depends on various factors. So MEM controller creates a memfd with given memory size and returns it back to QEMU. QEMU then can share this memfd with the, if there are vhost backend, vhost user backends, it can share with that also. And they can map this memory range in their address space. Second step will be that we need to register user fault FD for all the address spaces. So first QEMU will be doing it for its own address space, and then it will be asking vhost backend to register user fault FD on its address space. And that support is already there. We use it for post-copy live migration. Once user fault FD has been registered over all the address spaces, QEMU makes another call to MEM controller to store all those user fault FDs, and MEM controller basically can start polling over all the FDs and it will be listening for the page fault events. So after this initial setup is done, and QEMU should not touch memory range until both the steps are done. Now let's look at some internals of MEM controller. First one is VM memory swapper. And before going in detail about swapper, like one detail I wanted to give is that MEM controller will be maintaining a per page map, status map, like that has details like if that page is currently swapped out in memory or unmapped. And now what does a swapper do? Swapper will be basically scanning all the memory regions of a VM. It will be per VM thread. And it will be deciding a swap target for that VM. Swap target is how many pages we want to swap out at a given point of time. And swap target is chosen in such a way that we keep some margin over decided physical limit for that VM to take future page faults. And how physical limit for a VM memory is decided, it depends on multiple factors like what is overall memory pressure on the host and what is current activity level of that VM. For our experiments numbers which we'll be presenting today, like we are using basically using static limits. So once swap target has been decided, we decide which pages to swap out. And as of now, we are doing it randomly. Random may look like very poor strategy, but VM is not a process, normal process. So in cases, both guest because both guest and hypervisor will be doing swapping. So if both use common strategy of LRU, there may be double swapping and making performance even worse. So, but we are not claiming that random is the best strategy. We need a thorough investigation to decide best strategy here. Once we have decided which pages to swap out, that request will be posted to swapper pool, and swapper pool can have multiple page swapper threads. Usually we don't need multiple threads because usually swap backends are the bottleneck, not the CPU. But in some cases where we have multiple swap backends and we want to parallelly utilize all the backends, it can be useful. Also in cases where we have super fast swap backend, it can be useful because we have seen that there are some latencies with user fault FD. So to overcome those things, parallel swapper threads may help. Now, how a single swap out operation looks like. Like first thing we do is that we mark that page as swapping out in progress so that no one can parallelly update status of that page. Then we write protect that page with the help of user fault FD so that while we are in Windows swapping out that page, guest cannot write on that page or modify content of that page. Then we write that page to swap backend and free mapping for that page with the madwise syscall with the madv remove flag. And at end, we again unprotect the page. So with this, swap out operation is done, and we can basically mark that page as swapped out. Similarly, this is how swapping process looks like. Like there will be again a per VM swapping page faulter thread, which will be basically listening over all the user fault FD for page fault events. And if there is any page fault event, it will be again posted to faulter pool, which can have multiple faulter threads as per the requirement. And this is how a page fault operation looks like. Like first thing, we wait until that page status has been marked as swapped out or unmapped, because we discussed that a page can be in process to swapping out. So we have to wait until that window is over. Once we see that that page has been swapped out or unmapped, we mark that page as swap in progress, so that again no one can modify page state parallelly. Once that is done, we read, if it was a page fault due to write protection, we simply disable write protection. And in case if it was a page fault due to missing page and status of that page is swapped out, we basically read that page from backend and then use user fault FD copy IACTL to map that page in address space of guest. And then at end, we update a status of that page to map. We do some kind of prefetching also, like we do all the operations of page fault and swap out in group of multiple pages. That gives us two advantages, that we can basically avoid unnecessary page faults on nearby pages. And another advantage is that it reduces number of user faulty FD calls and read and writes from swap backend. So on average, for a single page, we get lower latencies overall. Now we have discussed about our new design in detail. This design gives us full control over page swap out and page fault decision. So basically, it gives us complete view of swap state of that VM. So with this advantage, like we already discussed, live migration with native overcommitted memory overcommit has some issues like slower migration, and because we have to bring in pages which are currently swapped out, so it makes live migration slow, and also it impacts guest working set size, working set estimation, making even both guest performance as well as live migration performance worse. So because we have a view of swap state, we can basically skip live migrating those pages which are currently swapped out, and we can directly map those pages on destination side if it is a shared remote storage. But even if we skip transferring pages or avoid pages on source side, there may be page faults on destination side, because swapping on both source and destination side works independently. So we have few strategies to avoid that also. Like first thing we can do is that data received on destination side during live migration is always the latest data. So instead of reading a swapped out page from backend, we can just map it with the 0 page. Another thing we can do is that we can try to keep swap state of both source and destination in sync by frequently sending some hints, so that chances are very low that a page is mapped on source but not on destination side. This second strategy is best effort only, because we may have different VM physical size limits on source and destination. So with these two approaches, we can try to minimize page faults on both source and destination side, making live migration much faster. So this is how live migration workflow looks like. First thing, what source QEMU will be doing, it will be asking source MEM controller for details about page status map. MEM controller will be sharing a page status map with QEMU with help of MEMFD. So now QEMU will have runtime status of all the pages, like which page is swapped out, which page is not currently swapped out. Based on this detail, while transferring any page, QEMU can check if that page is currently swapped out or not. If it is swapped out, we skip that page. There may be some races like if some page is swapped in, but QEMU may think it is swapped out, but that can be compensated by QEMU's dirty memory tracking in next iteration. And in final stage, we send all the details about skipped pages and source swap target to destination QEMU, and destination QEMU feeds this information to destination MEM controller. And now if there is any page fault on destination side, and if that page was skipped during live migration, we take that page from source swap target, otherwise we take it from destination swap target. And also there will be another background thread running, which will be syncing all the skipped pages from source swap target to destination swap target. And once all the pages has been synced, we can basically discard source swap target. So with this live migration workflow, this is complete view of live migration workflow. Now, Tejas will be talking about some numbers we have obtained with different experiments.
Thank you. So coming on to the results of some experiments which we have done, these experiments range from various experiments across running workloads on VMs with different types of swap backends, also real-world workloads, and a live migration scenario as well. So the first graph which you see here right now is a throughput comparison for a synthetic workload which we're running on the VM. The VM's swap backend is a slower SATA SSD. The VM's configured here with 12 GB of memory, and the workload which is running inside of the VM is a synthetic in-house workload which aggressively dirties and allocates memory. And its working set size is like roughly around 10 GBs, which is enough to ensure swapping inside the VM. On the y-axis, you see the throughput for the average throughput for the workload in megabytes per second, and on x-axis, you see the swap ratio. So by swap ratio, I mean the ratio of the memory of the VM, which is swapped out to the disk upon the total memory of the VM. So essentially, if it's a higher swap ratio, you will see more level of swapping activity inside the VM. So across all swap ratios, we can see that from going to the native Linux memory overcommitment to our user fault FT-based approach, we are able to see 2 to 3 times improvement in terms of the average throughput for the workload. This can be primarily attributed to the reason that in the native Linux swap subsystem, we've seen that even if you set the page cluster value to a higher value, let's say 16, it issues 16 individual rewrite requests. Whereas in our scenario, we do rewrite requests in large IO block sizes. So this helps us immensely, especially in this case where the memory access pattern of the workload is much more sequential in nature. Coming on to scenarios where the swap backend for the VM is our faster devices, for example, compared to the previous one. So what we have seen in our experiments is that even though we get good results for slower swap backends like SATA SSDs, the overheads of using user fault FD become much more significant when moving over to faster swap devices. For example, in NVMe, you can see that we are only able to see a 20% gain as compared to 2 to 3 times before. And when going from a RAM disk-based swap backend, we see around like an 8% regression. Yeah. So that was all about synthetic workloads. Now coming on to some real-world workloads, the first one which we tried was the Redis in-memory database. So the VM here is a 5 GB VM, and the database is configured so that its working set size is around 2.5 GB, which would ensure swapping inside the VM as well. And after the database has been loaded into the memory, we do a bunch of operations in it, 50% of them being read operations and 50% of them being update operations. And then we observe the average operations per second for that workload. And we can see that from going to the native Linux subsystem to the memory controller approach, we are able to see a roughly around 20% gain in terms of average ops per second. Another real workload which we tried out was kernel compile. Kernel compile turns out to be a bit different. So kernel compile has a really low working set size, so we had to configure the VM in such a way as well. So it's a really tiny VM and squeezed to a really small limit. And in the end, we ended up seeing roughly a regression of 8 to 10% when going from native Linux subsystem to memory controller. So the conclusion here is that, as we've seen before, that even though our approach works really well for workloads which are more sequential in nature, even for non-sequential workloads like kernel compile and especially Redis, we are not that worse. Coming on to the live migration performance. So the VM here is a 12 GB VM, and we are trying to live migrate from one host to another host. And the workload is the same as mentioned before. It's a synthetic one with a working set size of 10 GB. So as my colleague mentioned before, that we end up skipping, we have the control of the swapped out pages, so we can just decide to skip instead of transferring them over to destination, which helps us save a lot of time in terms of time to migrate. For example, in the first graph, you can see that the time to migrate reduces by around like 4.5 times when going from native Linux memory overcommitment to memory controller approach. We can see similar gains in terms of data transfer during the migration as well, but the magnitude is not that much because the swap ratio here is 0.5, which would essentially mean that roughly 6 GB of your VM's memory is mapped into the memory, mapped, and you essentially have to send it over to the destination anyways in both cases. So So to conclude, we've seen that a lightweight-based, user fault FD-based memory controller approach works really well and gives us a significant performance improvement in the memory overcommitment VM's runtime performance. We've seen that our approach is performing well for slower swap backends, but it kind of bottlenecks for super fast swap backends like NVMe and RAM disk. We still need more exploration for how to evade these bottlenecks, right? Also, since we have control over the whole swapped out pages, we can just avoid page thrashing inside the VM during live migration and also enable faster live migrations. So coming on to the bits of what we have still need to do, right? So as I discussed before, our solution doesn't scale well with super fast swap devices. And one thing which we've seen is that the cost of calling user fault FD operations increases with the number of shared memory address spaces. One way which we can go around this is by having parallel faulter or swapper threads, which can reduce the average cost for each of this call. Another way which we can go around this is having a larger swap granularity, which can also reduce the average overheads. Another thing which we have seen is that there is a large latency involved in context switches. So the user space has to do syscalls whenever it has to read a page or handle a page fault, right? So, and syscalls are eventually costly. So we need to investigate on some new approaches on how to handle and acknowledge these events. One of the ways which we can do is probably having like a shared memory IO ring between the kernel and the user space so that both can communicate for the events. We can also try to avoid an extra memory copy whenever we call the UFFD copy ioctl. And lastly, we saw that there is a very high latency involved in whenever we do the madv remove call. And since this call essentially locks the memory address space of the VM, even having parallel faulter or swapper threads doesn't help you. So we need more efforts to make it faster or evade this, right? Yeah. And lastly, as my colleague mentioned before, our design doesn't account for memory ballooning inside the VM. Currently, ballooning is managed by QEMU, and whenever a ballooning event happens, QEMU does the following. So on an inflate, it will call a madv remove, and on a deflate, it will call a madv will need. Since our design works on the fact that no other process or service can modify the memory address space of the VM, we would need to handle these events in some way. So one of the ways which we can do this is probably by telling QEMU to process the virtio balloon rings to send all of those ballooning events directly to the mem controller service, which we have done, or it can directly share the virtio balloon rings to the mem controller service so that they can process the events directly instead of going through QEMU. So thank you. That's it from us. And if you guys have any questions, comments, suggestions, please go ahead. Yeah.
Okay, I don't have that much time. We have like a minute left. But I'm a little bit concerned with MNV remove. Like, I think that can succeed even if there's a pin still on the page, like if the ref count is still raised. So something might still be using it. So that's a little bit concerning to me. I'm curious what you think about that, but I have a couple more questions. Do you do working set estimation for user space, like for the user?
Currently, we are not doing that, but
okay.
We have planned to do that. Yeah.
Okay. I would suggest maybe doing it with user fault FD minor faults, so you can unmap it from the page tables and then leave the page in the page cache, and then you can map it again.
Sure.
Yeah, I think that would be pretty cool. And also, Google avoids the swap out thing, it avoids sending the swapped out
events.
We use a special syscall. It's not upstream. It really should be, where we query the swap state of the file before starting the live migration, and then reapply it on the target. I'm not sure if that would help you guys in this case.
Okay. But we investigated similar approaches like internally, but that was making things more complex. And
okay. I think this is less complex than the user fault FD thing, but whatever.
So one comment. I think you mentioned that you're swapping in pages with a UFFD copy, and that sounds like a big overhead. There is a way to achieve it without, with a zero copy. Like you can actually copy when you're reading data from the disk. Mm-hmm. You can pretty much put it in memory and then like resolve with zero copy.
Okay.
I think you use UFFD continue to circumvent that. And another question is like for the policy, you are using random. Like, do you have any plans how to, because, random, okay, fine if you're trashing, but trashing in the cloud is a very bad idea. So most of the time what you want to do is find what is cold, because there's a lot of cold memory. So that's what you want to focus on, right?
Yeah.
So do you have any plans of how to identify the cold memory?
Like we mentioned, we currently don't have any user space VM memory activity tracker. So once we have that, we can definitely track which pages are cold and which are not. But like I already mentioned, guest can have guest level swapping also. So LRU still may not be the best policy for guest
but
specifically.
Cold is cold, right? Like if it's not touched by like 10 minutes, like there's no LRU, right?
Yeah, but assume a page was detected cold by a guest also, and it has swapped out that page, and it brought a active page there, and now hypervisor level, we think that it is a cold page, and it can again swap out. So that kind of double swapping issues can happen.
Yeah, I mean that's slightly different, but okay. So one more question. You didn't mention the page size. You're working with 4 kilobytes, 2 megabytes?
For our experiments, we found that a page group size of 4 pages works best for most of the cases. So
4
we are using 16 KB.
Okay. And do you have maybe some numbers for the overhead? Like how much overhead did you get with the, doing everything user space? Like, reading a page, whatever, 70, 80 microseconds, like how much do you add on top of that?
Like you are asking about user fault FT latency or swap backend read?
Yeah, like, to go to user space to do like some logic to pick a random page, whatever, like how long does that? Or like, just processing the user fault FT instead of doing it in kernel. Do you have some maybe numbers, like how many microseconds?
Those were in magnitude of thousands of microseconds. In that range, it will be. Cost of user fault FT, individual operations were in that range. Yeah.
Okay.
So that's why we were bottlenecking around a throughput of 600, 700 Mbps. So if backend is faster than that, we were bottlenecking.
So it's like you're saying 1,000 microsecond, but that includes also the I/O path.
Not I/O path.
Just the overhead that you're adding, or
I'm talking about individual calls. Like there are multiple calls in a swap out path. Now you have to write protect it. You have to madwise remove. So each one of those were in that magnitude.
Because I think from kernel, like the whole thing takes like 20 microseconds or like even less. So, and then if you're doing it in user space with 1,000, how does it like your result look so good?
Thousands of nanoseconds, not microseconds.
Okay. Okay.
I think we're pretty much out of time, so I'll take 10 seconds. The first is squeezing VMs as hard as you were squeezing them cause a big performance difference compared to non-swap. The swap performance needs to be almost indistinguishable from non-swap in order to have customers actually adopt this. You can already see whether pages are swapped or not from the proc PID page map file. You don't need a whole bunch of user space additional tracking. You can use that page map to drive your first pre-copy cycle.
Okay.
And I forgot what my third point was. You can almost certainly develop some mechanism to copy across the swap data to destination droplet, and some general aging out process is useful in the kernel independent of VMs or user space applications, like have multiple swap tiers that the kernel can implement for everyone.
Yeah. So like we mentioned, there are multiple advantages. One is live migration. Other can be like with native Linux system, we are observing very low swap throughput. So that is something also we wanted to optimize. So that's why we wanted to take control in our hands with user fault FT. But I agree with your point.
Okay, we are over time, so thank you.